So now are we recording? Okay, so now that I remember to actually start the recording, I'm recording these lectures, and they're all going to be posted on YouTube soon after the lecture ends. So I'm going to try every evening when I go home to get it out online on YouTube. So that means if you feel like leaving at 9 o'clock because you're exhausted and you've had a hard day at work and you want to get some sleep, that's fine. I will keep lecturing, and I, of course, will not get offended if you leave at 9 o'clock. And you can watch the remaining hour the next day on YouTube. And I thought that's also something that would be useful for folks to have the YouTube lectures. These are not going to be public YouTube lectures. I will be sending out private links so that only you will have access to these videos. And you mainly, namely you people, you folks. We don't have a possessive plural. We don't in English, but y'all in the class. All right, we could use the word y'all. All right. Virtual office hours. So since we're an evening class, it's kind of hard for a lot of people to come to campus again for office hours, especially during the day, since a lot of you are working during the day. So what we're going to be doing is holding virtual office hours Thursday evenings from 10 to 11 p.m. via Zoom. And if you haven't used Zoom before, that's fine. It's becoming probably one of the most widely used video conference apps out there. It's really good. It's really high quality, and for you, it's completely free to use. It runs on your phone or Mac OS or Linux or Windows or pretty much anywhere, and you can download it. And this is the link up here that we'll be using. If you can't make it by video, you can dial in by phone just to do audio. But of course, what happens a lot during office hours is I share screen. And basically, I write on the screen, and I write notes, and I post the notes afterwards to our webpage, which I will talk about in a second, so that you get access to at least the handwritten notes that I've done during office hours. A few people have asked in the past if I could also record the office hours. I'm usually not doing that. I usually don't record the office hours. But if you find it absolutely necessary, I can probably do that too. A lot of people. One of the things about recording the office hours that a lot of people don't like is that when I use Zoom, and I usually like to have bidirectional video for the office hours so that you can see me and I can see you. But if I record that, then your face also gets recorded. And a lot of people don't like that. I don't personally mind it, but other people mind it. And so fewer people end up coming to office hours. And that's one of the reasons why I don't usually record office hours. The other thing I want to mention is that if you need other help besides these office hours, I'm happy to open up other slots. You can send a message on Canvas, and I can virtually meet you other times. But this 4-hour span on Tuesday nights will be each week the only time that we meet each other in person, and the rest of the time will be virtual. Our webpage, we're actually using Canvas, and you can actually go there now. It's live. Usually, by the way, these slides that I'm lecturing from, I'm usually going to be posting it. In fact, I'll do it at the break. I'll be posting these slides to Canvas before lecture, so if you have a laptop or a phone or something, you can be annotating these slides as we're going along. I haven't yet done it today, which is unusual for me, but I will do it during the break, because I had to rush over here from something else. And the other thing I want to mention is that when you have questions, so rather than emailing me in person, you can do that, but I strongly discourage it, because usually your questions are very good, and usually when you ask a question, half the other people in the class have that same question, and if you ask it publicly and it gets answered publicly, then everybody else benefits from the answer to the question that you asked. So please do use Canvas to ask all questions. Now, one of the reasons why people don't like to use Canvas for asking questions is that it is public and maybe they're embarrassed. It's something you shouldn't be embarrassed about. Something I always say, and this sounds this might sound trite, but it's actually true, that the only bad question is the one that was not asked. So if you ask a question, that renders it a good question. So, and like I said, if you have a question, chances are half the other people in the class also do. It's just the way things are, and people don't realize how much, or I should say, people don't realize how much other people in the class that they're in with know. So after all, we're here to learn. Okay, so we have two teaching assistants in the class. The first on the left is Chandrasekhar Lavanya. And he's actually not here yet. He'll be, I think he's coming back in a few days. And the next person is Niraja Abhyankar, who's sitting at the back. Maybe Niraja, you could stand up and wave to Niraja. Hey Niraja, how you doing? So they will also be having, probably, are you going to do virtual office hours or physical?
Yeah, we haven't discussed it yet, but I posted an announcement last week, so.
All right, okay, so yeah, there'll be virtual, probably virtual office. I mean, we can use Zoom also for that, but we'll post that. We can organize that through Canvas. So there will be other times that you can meet these folks. And Niraj actually TA'd for me last quarter and did a very good job. And so I think that you're in good hands with us three, I think, at least I hope. Okay, so let's just do some more logistics. By the way, these slides, as you can see, we have, the sections are up here on the top, and you can see how far along we are in the section based on the highlighted white vertical little bar. So we've got maybe about five more slides in logistics. So, prerequisites, as I said, you should have some knowledge in probability, statistics. Some linear algebra is important. If you don't know any linear algebra at all, it's going to be a little bit of a struggle. You should have some calculus, multivariate calculus. And ideally, although it's not absolutely necessary, you should have some information theory and some mathematical optimization. But we will be learning that as well as we go along. Now, you don't really need to be an information theorist, or you don't need to have taken an information theory class, but some of the concepts from both information theory and, of course, mathematical optimization, which is fundamental to all machine learning, as you will learn, is helpful. With regard to a textbook, we're actually not going to be using a physical book. So that's good and bad, right? It's good because it's not an expense, an additional expense for you. And in fact, to be honest, it's only good because right now we're going to be using these slides, and these slides are pretty self-contained. These slides actually are not only what we lecture from, but they also offer essentially lecture notes from what we've talked about. They're pretty detailed. And then the other thing is that a lot of times the slides will post to free additional online resources that you can use to read up additionally. So I will post papers and tutorials and other lectures and things like that will come as the class proceeds. Pretty much, there's so much online tutorial material in machine learning these days that we can save the cost of a textbook. Although I will be making some recommended readings in a minute. There are a couple of textbooks that I think are worth owning for additional reading, although we're not going to have assigned readings from any of these textbooks. But if you went and bought them, you would be in good shape. Grades and assignments. So we have about 5 or 6 assignments this quarter. There's 10 weeks, maybe one assignment roughly every 2 weeks. And your grade is based entirely on your homeworks. And now these homeworks are going to be fairly substantial. They're going to be a lot of work. And they will consist of both a combination of sort of mathematical problems, which you just work out on paper and pen, and also some large programming assignments. And like I said, the programming assignments are done in Python, and you have to do them in Python. They're going to be released as Python Jupyter notebooks or IPython notebooks, whatever you want to call them. And you're going to be essentially filling in the notebooks and turning in a notebook file, an IPNB file, or whatever they're called, IPYNB file, as part of your solution. And grades are going to be based on these homeworks. There's no in-class exam. There's no in-class test. There are no pop quizzes. There's no final exam. But what's really important to remember is that the grade is based on the quality, the clarity, and the correctness of your homework assignment. So clarity is important, right? So if we can't read your solutions, we can't grade your solutions, so we don't know if it's correct. So clarity is important, and neatness. And of course, it has to be correct, and it has to be high quality. A little bit more, so on the homework. So homework must be done individually. So everybody in this class needs to individually turn in their own homework assignment. And each student in the class needs to hand in their own answers. And also each student must write and submit their own code. So it's your own code that you've worked out yourself for the programming part of the assignment. And we will run and test your code. One of the nice things about Python, Jupyter Notebooks, is that it's very easy for us to run it and see if what you wrote works. And that it's a beautiful way of doing programming assignments. However, it is acceptable to to collaborate, to talk to other people. It's not like you're competing with each other, with your colleagues here in this class. It is acceptable to talk to each other and say, hey, Fred or Sarah, how did you guys do this? And then maybe Fred and Sarah will get together and chat over coffee about one particularly difficult math problem that they've got. But the solution has to be written yourself and in your own words. We're going to be looking for copied solutions. So if you copy one solution from somebody else, we're going to spot that. The other thing, of course, you can ask questions on Canvas. And when you ask questions on Canvas and they get answered, that everybody benefits from those questions and the answers. And of course, everybody could get benefits from the answers to the homeworks for their homeworks. Homeworks are not going to be sort of synchronous with the lectures. Since we have an electronic communications medium, you'll be receiving email. What I would suggest you doing is going to Canvas and making sure you get email every time something is posted. There are actually some settings in Canvas where it says post, a daily digest or a weekly digest. You don't want the weekly digest. You don't want the daily digest. You'd like ideally to get an email as soon as something is posted. And there even purportedly is some way of getting a text message when something gets posted, but I personally have never been able to get that to work for me. But you can get can get an email. And the other thing is we're not doing paper, so all homeworks need to be submitted electronically. So that means you can write it out on paper and pen or whatever, but you have to take pictures or somehow convert it into a PDF file that you upload. And so therefore it means that you need to take reasonable quality pictures. And there are lots of online PDF converters that take a string of photos and convert it into a PDF file. But basically we'll be accepting only PDF file. In fact, what the homework consists of is every homework will be two files: a single PDF file that contains all of the answers to your math problems, and then and maybe some plots, and then when relevant, and which will essentially always be relevant, as a single zip file with any code or data or the IPython notebook file, right? So there'll be two files: a PDF file and a sort of grouped together zip file which contains everything else. And so we'll only accept PDF one, and make sure it's only one PDF. So don't stick like PDF files in your zip file, because the nice thing about the PDF is that we can actually grade them using a Canvas tool, and we can actually mark up the PDF, and you will get your grades much more quickly if we can actually mark up the PDF directly in Canvas rather than having to explode the zip file and mark it up in some other way, and you won't get the feedback nearly as quickly that way. Right, so I said like lecture slides will appear on Canvas before the class begin, except for today. And updates, so basically any markups, like sometimes, this actually happens fairly frequently, like I will do additional drawings, especially in response to people's questions. I'll be drawing them on these slides, and anything I draw will be posted after a lecture to Canvas as a PDF file, and you'll also see the YouTube recordings. So like if there's, I don't personally have very good handwriting, but if you particularly like a picture that I draw, which you won't, but if you do, you will get to see it again, even if you missed copying it down. One other thing that's very important is the University of Washington has a special provision for religious accommodations. And basically, this is a policy associated with religious accommodation that the University of Washington must and does abide by. And let me just read this very quickly. Washington state law requires that UW develop a policy for accommodation of student absences or significant hardship due to reasons of faith or conscience, or for organized religious activities. And the UW policy, including more information about how to request an accommodation, is available at that link. And accommodations must be requested within the first 2 weeks of this course using religious accommodations request form, which is available at the second link. Basically what this is all about, this is a policy of respect. And I personally like it because it basically means we respect diversity. And it's something that I think is important, something that you should look into if this ends up being something that you want to use. One of the things, however, in this particular course that is particularly useful for you is that since we are recording these lectures and posting them on YouTube, if you have to be absent for some reason, you're not going to miss hearing the lecture, because it will be on YouTube. You will get an email about it soon after the lecture, And so you won't miss anything, so you won't miss out on the class. So you can not only see the class multiple times, you can make sure that you never see the class 0 times. Okay, some other logistics. This is just on the slide format. I just want to mention something about equations. So like here's a typical equation right here, right? And so the equation has an equation number. Oftentimes we can refer to an equation number of the equation. It's very useful. The first number in the equation is the lecture number. So if we say 1.1, that's the first equation in lecture 1. Okay, so that's L.J. And sometimes we see things like L.S.J. So it would be the lecture number, the section number, and then the equation number within that section. So that makes it really easy to refer to specific equations. And we will be using equations, right? So we need to use equations and math to explain the concepts that exist in machine learning and AI. And similarly, things like theorems, lemmas, and postulates, and those sorts of things will use similar sorts of equations. Like here's the first theorem in section 1 of the first lecture, Froux's theorem. There's one exception to these rules, is that starting next lecture, we will have a review section. And everything in the review section will be identical to the previous week's slides. So one of the things that's actually quite useful to do, especially at the end of the lecture, is you could just watch the review of all previous lectures and get kind of an accelerated version of the whole class just by watching the review of each previous lecture. Because each review will probably last about 5-10 minutes. And that way, that's also a good way of looking at the outline, and you could just copy the slides, say, from the review section of the slides from all the previous lectures. The only lecture that we won't review, of course, is the last lecture, because we only have 10 lectures. We don't have an 11th lecture to do the review of the 10th lecture. Okay, and in fact, here are the 10 lectures and our dates. So today's the 7th. Our last lecture is on the 10th of March. The last day of instruction of the quarter is the 13th. Finals week is the 14th through the 20th, although we don't have a final exam, so we have 10 lectures. And this is essentially our syllabus, or our outline. Pretty much everything associated with the class will be on these slides, like syllabus, lecture notes, everything are these slides, these PDF slides. And these slides, you're free, of course, they're yours, right? You keep them, and you can do whatever you want with them. When you're done, you can print them out and burn them if you want. Or you could use them as Christmas ornaments next year, whatever. They're yours. So today, what we're going to do is, talk about machine learning. What is machine learning? We're going to talk about probability, coins. We're going to do a very simple machine learning problem associated with coins. We're going to talk about multivariate Gaussians and linear regression and linear least squares. We're going to also talk about what an associative memory is. and then begin talking about supervised learning. And also, I think we'll probably get a little bit on gradient descent. We'll probably, by the end of the lecture today, we'll talk a little bit about that. And then the rest of the topics are for the rest of the quarter. Now, it's possible that these might change. If we don't make it through everything we wanted to do today, we'll cover it next week. But this is our goal for the class. Okay, any questions? That's the end of logistics. Any questions about logistics? Yeah.
Are we going to cover neural network?
Well, that's a good question. You want to cover neural networks? So neural networks are obviously one of the key reasons probably why you're here. And you notice that you haven't seen neural networks on this thing. So who cares about neural networks, right? So machine learning is a lot more than just neural networks, right? And there's a lot of machine learning concepts and fundamentals that are necessary to even begin to understand neural networks. So I do teach a neural network class. And in fact, I have a whole separate 10-week class just associated with neural networks. And last year, I taught the 10-week machine learning class and then the 10-week neural network class. And so I deliberately didn't include neural networks in the 10-week machine learning class because I knew we were about to have 10 weeks of neural networks. And by the way, even with 10 weeks of neural networks, we still didn't really talk about everything associated with neural networks, right? So neural networks is itself a complicated topic, or I should say it's an involved topic. However, I'm planning to teach the neural network class next spring of 2021. So I'm not teaching the neural network class this spring. So I probably will add some neural networks to these slides. But obviously we're not, this is still sort of a fundamentals class. this class will give you the tools that you will be able to use to understand many of the concepts that exist. Because neural networks are just one additional model, as we will see, or one additional class of models, as we will see. And you can't really understand neural networks without understanding these fundamentals. Okay, any other logistical questions? Yeah.
Are we taking out anything from there to do the neural network?
I hope not. I hope not. You know, emphasis on the advanced part, right? The advanced introduction. We're going to do a lot of stuff. So I'm going to try to squeeze it in. Yeah, I can't imagine taking out anything. I could take out the future. Okay, so that means we have to go a little faster. Any other questions, though, on logistics? Okay. By the way, so like I said, it's a 4-hour lecture, but we take a break after about 2 hours. So for about 5 minutes. Okay, so here's today's planned lecture. You can see to the sections up at the top, and we're going to try to get through all these little sections in the next, however many, 3.5 hours. So there are a lot of companies that are investing heavily in artificial intelligence and machine learning and data science. And that they include companies that are well known, like Google and Intel and Amazon and Facebook and Salesforce and Twitter, but also other companies that are perhaps less well known. I'm not going to mention any names, but you can see that there are a lot of companies that are specializing in AI solutions to various different problems. And probably the reason why you're here is because you want to, be involved in the excitement that's going on. There's a lot of excitement that's going on right now in the world of AI. And AI is now doing and achieving things that historically it's never been able to do so far before. So one of the things we want to learn in this class is what's different. Like, what is it that has happened over the past? It's really 10 years, but it seems to be still increasing very rapidly. That the ability of artificial intelligence-like solutions to certain problems seems to currently show no end. And we'll talk about that. Our class, what we're trying to do, and this isn't meant to be a serious slide, so don't really start reading this. This is the description, the textual description that went out to you guys to describe what the class is about. And when you read it in this form, it just looks like a grab bag of techniques. What we really want to do is sort of organize it in some way. And so this is kind of a sort of synopsis of all things machine learning and AI. And what I'm hoping we get to, we have the syllabus from a few slides ago, but I'm still hoping that we do what we get to is that when you get to the end of this class, everything on this list will be clear to you. And so let's zoom in on each of the sections. So we've got 12 different little sections. So we're zooming in on section 1, which is, of course, what is machine learning? Like, what is it that machine learning does that renders computers so capable that other computational methods haven't been able to do? And why can they achieve that? And what is artificial intelligence? Is it real intelligence? Are robot overlords about to take over, and Skylab and Terminator and Arnold Schwarzenegger's about to take over the world? Or is it something else, and perhaps a lot more mundane? And why are we so interested in these topics right now? I mean, that kind of question we want to touch on. And then we want to sort of talk about, there are these different kind of categories. Let me just mention the categories first. So there are these different machine learning paradigms and concepts. There's ways of dealing with features. First of all, what is a feature? How do we evaluate systems? How do we achieve a learned model? Like why do we call it learning? And essentially learning is optimization. What is a model, and what are some models, and how are things being represented? What are some ways of computing probabilities? I think I skipped 6 and went to 7, so I'm going from 7 back to 6. We'll talk a little bit about philosophy, humanity, and perhaps even the spirituality behind artificial intelligence and what that means. Some applications, and there are lots of applications. Programming paradigms. We're not going to actually have a section on this, but there's a lot of background associated with machine learning and AI. And lastly, some other techniques as well. So there are a lot of different things, and what I would suggest doing is, I mean, I could just list all of these, and if I went and I talked through all of these different things, at this point it probably wouldn't make any sense. It would just be a bunch of buzzwords and terminology that folks wouldn't get a lot from. But let me just scroll through and see and sort of describe what each one is. So there are a lot of sort of strategies or settings or paradigms or techniques for achieving a machine learning system, and that's what paradigms or concepts are. Like, for example, supervised versus unsupervised versus semi-supervised learning. We're going to be talking a little bit about supervised learning today. But there are lots of other sort of learning strategies. And some of these we're not even going to get to until the last lecture, because a big part of what's happening in machine learning now is developing new paradigms for learning. Like, there's lots of different ways to learn. Should we learn the way humans learn, or should we learn based purely on mathematical optimization, or should we do some sort of hybrid? There's a lot of really interesting stuff that's happening right now in the machine learning world on just how do you learn. And that's kind of the paradigms. Another big part of machine learning is features. So, features are basically a way of representing data. So, and what is data? Data, you can think of data as any sort of raw sensor output or raw records in a database system or in a table or in a spreadsheet or something. The question is, do you just feed a row of an Excel spreadsheet to a machine learning system, or do you do something to it first? Do you transform it into a representation that the machine learning model likes better or can deal with better, or what that really means is work better with? And that's the whole process of feature engineering and feature extraction. And so we're going to learn something about feature extraction methods, and there are a lot of different methods, from PCA, principal component analysis, or linear discriminant analysis, and so many other different methods. Neural, bottleneck methods and neural networks. There are lots of methods for doing that. Evaluation is also critical for machine learning, because one person might evaluate a model and say, this works great. And another person might evaluate the same model, and say, this works terrible. And so you have one person saying it works great, the other person saying it works terrible. Who's right? Well, it's because they're using different evaluation methods. And so you need to understand, you need to be able to evaluate evaluation methods to decide how do you want to be able to tell whether what you have learned in a machine learning system is good. And that's the idea of evaluation. So there's a lot of different components to this. There are things like, do we use accuracy? Do we use error? Do we use things like precision recall curves, or ROC curves? Do we use like likelihood-based evaluation? And then also just what data do we evaluate it on? Do we evaluate it on the train? There's data, and data has to be divided into different sets, used either to train or to evaluate or to test on. And how do you divide these data sets into subsets to evaluate on? And that involves things like cross-validation and bootstrap and so on and so forth. So evaluation is really critical. Another thing that's quite critical is optimization. So a big part of machine learning, you can't learn about machine learning without learning about mathematical optimization. So what mathematical optimization is, it's something that actually comes from pure mathematics. It's basically saying, you've learned about it in your calculus classes. When you want to find the root of a polynomial, and it's a big polynomial perhaps, you need to use numerical methods of some sort. Or you want to find the minimum of a function, right? Like when the gradient is equal to 0. Those sorts of things you use mathematical optimization for. And there are lots of different methods for doing those sorts of things. And machine learning is kind of almost exactly the same, except these are much, much bigger systems. Rather than actually a curve that you can plot, and we will be using curves, but rather than a curve that you can plot, you might be optimizing over hundreds of millions of parameters rather than one or two parameters. So we're potentially operating in extremely high dimensional spaces and doing mathematical optimization in these extremely high dimensional spaces and using ridiculous amounts of computational time to do that. It's crazy when you think about how much compute is spent on learning some of these systems, not to mention how costly it is. Some of the more modern machine learning systems cost anywhere from $50,000 to $100,000 just to develop a model. And every time you develop a new model, you might need to spend that much money again. And so that's a big expense in order to get a model, of course, that works. Now, you're not going to need to spend $100,000 for each homework, obviously. But you might start getting a taste of of just a taste of why it's challenging and why optimization is challenging. And there's lots of different optimization methods as well. There's continuous, unconstrained continuous optimization. Stochastic gradient descent is kind of our workhorse, or gradient descent, and various different learning rate adaptation schemes and so on. There's also constrained continuous optimization, a big conditional gradient or Frank-Wolf-like methods and so on and so forth. And then there's discrete optimization methods like the greedy algorithm works a lot, and beam search, and so on and so forth. Mathematical optimization is kind of like the heart of machine learning, and you'll see why. And we will touch a little bit on some of the stuff in the mathematics community. Inference, it's kind of interesting. You might say, okay, well, what's the probability of A given B? And you might say, well, it's just that probability, but it might be very hard to just compute that probability. And computing these probabilities is oftentimes what you need to do optimization. And so we will talk to some extent about probabilistic inference and how do we compute it and how do we make it more efficient. Because if we weren't smart about how do you compute probabilities, that $100,000 cost to train a model might suddenly become a $100 million cost, or $100 trillion cost, or essentially it would take hundreds of millions of years, because we're dealing with an exponential problem potentially. So we have to deal with figuring out how computing probabilities can be done quickly. And then of course there are lots of different models. I think neural networks should be here somewhere. Does anyone see neural networks? Yeah, there we go. It's right here. Neural networks and deep neural networks. So neural networks and deep neural networks are just one of many different models. What we will talk about is random forests and gradient boosted decision trees. And so, by the way, in this class, and we will talk about it quite extensively. Gradient boosted decision trees and random forests are probably the second most popular method for doing a lot of machine learning tasks, and people use them a lot in practice. Because first of all, they're a lot faster to train than neural networks, and they actually work pretty well. Oftentimes they even work better than neural networks. And so we will talk about this kind of stuff. But there's lots of other methods as well. And in order to understand what machine learning is, we have to spend some time on linear least squares. In some sense, these are the simplest of models. But if we don't understand linear least squares, we'll never understand neural networks or random forests or anything else. And this also includes like time series models, by the way. It's like hidden Markov models, dynamic Bayesian networks, and recurrent neural networks. Those are also model families. We'll probably briefly touch on what a hidden Markov model is. We're not going to have a lot of time. But maybe you've heard of hidden Markov models. They're also quite important. We're not going to have a section devoted to, the philosophy and societal consequences of artificial intelligence. But I think by the end of the class, you'll get a sense of my own personal beliefs about that. I mean, I personally don't think. I'll say it right now. I don't think we're anywhere close to achieving anything close to human consciousness with any sort of artificial intelligence. Not even close. Not even the slightest bit close. We can't even get a vacuum cleaner to vacuum properly, or a printer to use ink properly. And people are worried about artificial intelligence achieving human-like intelligence. We're not close. There are some societal consequences analogous to how the Industrial Revolution, when it came into existence, displaced a lot of people who were working on certain things, which became redundant because machines were able to do them more efficiently. It's not that we're about to have a conscious being from artificial intelligence, but it is the case that there are some jobs that people are doing that might get replaced by some sort of computer program, essentially. And so there's going to be some job displacement, and that is something that we should worry about. And that's a much more tangible societal issue to worry about than the science fiction Terminator kind of scenario, which we will not see probably for 500, 1,000 years, if ever. So Of course, there's a lot of applications in biology, in social networks, and computer vision, and speech. Speech and language processing is very popular these days, and everybody uses speech. There's Siri, there's Alexa. It's here. People are using this stuff on a daily basis. Google Home. We'll talk a little bit about how some of these things work as we're talking about techniques. And then our programming paradigm. Like I said before, we need to be an expert in Python, and some of the Python libraries that are very popular, like NumPy, SciPy, Matplotlib, and sklearn, and maybe a little bit of PyTorch, and possibly some TensorFlow and Keras, and maybe some H2O. But most of the stuff that we'll be doing will probably be sklearn based. Maybe if we do a little bit of extra stuff on neural networks, we might add some Keras or something. And then also, we're not going to actually ask you to do any programming in C or C++, but if we really want to achieve high performance computing, HPC, Python, you can get only so far with Python, but if you really want to get a core library to work efficiently on the machine, you need to use C or C++, or some sort of CUDA vector programming, to get GPUs to be efficient. So you still can't step too far away from the machine for too long if you're wanting to do something different. And then for some background, like I said, linear algebra, calculus, some probability and statistics, and so on and so forth. And then other techniques, like we might talk about compressed sensing, and then submodularity a little bit. Actually, I mentioned that here in the discrete optimization. Submodularity is a technique that's useful for modeling things like diversity in data. And we might touch on that. Anyway, so that's kind of an overview of what hopefully you will learn. And actually, the end of the last day, we're going to come back to this slide, and maybe what should be here's something maybe you guys can do now. If you have any notes, write down to yourself. You don't have to turn this in, but just write down what fraction of the things that you understood from this slide that I just said, and then in 10 weeks from now, at the end of the class, write down the new fraction after we go through this again, and hopefully it doesn't go down. Right? So. Okay, so how do we achieve a machine learning system? So, one way you could do is you could go to one of these like machine learning tutorial sites and use the machine learning cheat sheet. And so this is a machine learning cheat sheet that you could use. And okay, so it's kind of like a flow chart, and says, okay, I want to do machine learning. Okay, well, I should start at the beginning, right? So I start here, and so then I say, okay, well, do I need to do dimensionality reduction? And oh yes, I do. If I do need to do dimensionality reduction. If I'm doing topic modeling, is yes, and if it's probabilistic, yes, then I should do latent Dirichlet allocation, or latent Dirichlet analysis. And if it's not probabilistic, I could do SVD, or singular value decomposition, or otherwise, if it's not topic modeling, I do principal component analysis, PCA. And then after I'm done with my dimensionality reduction, I check, do I have responses? So like, is it a supervised learning or an unsupervised learning problem? And if the answer is no, I don't have responses, then it's unsupervised, and I have to do some sort of clustering of some sort. And do I want to do a hierarchical clustering? Then yes, I do hierarchical clustering. And if I need to specify the number of clusters, then and if I have categorical variables, I could use either K modes, or if it's not categorical, I could use K medians or K means, or if I prefer some sort of probabilistic interpretation, I'll use Gaussian mixture models. Or if I don't need to specify K, maybe I'll use some sort of Bayesian-like method, or something like dbScan. But that's all if I don't have responses. If I do have responses, then I can, if I'm predicting numeric, then I do some sort of regression. And if I care about either speed or accuracy, if I care only about speed, I would use a decision tree or a linear regression. And if I care about accuracy, I'd use a random forest, a neural network, or gradient boosted decision tree. And if I don't have numerical features, then if I care about speed or if I care about accuracy, I would use one of these techniques, like a random forest or a kernel SVM, or a gradient boosted decision tree or a neural network. And if I care more about speed and I care about explainability, maybe I'd use a decision tree and logistic regression. Otherwise, if the data is too large, then I use naive Bayes. done. That's it, right? So these kind of things you see out there are gross simplifications, and you can almost never really use. It's kind of like this is a caricature. I put this up because you do see a lot of these things in pop machine learning Medium articles and things these days, but it really is kind of a caricature of what really has to happen. You really do have to think very deeply about each problem. You have to really get to know each problem that you're trying to solve, and you have to ideally really understand the data that you're working with in order to get a machine learning system to work well. And it takes time, and I would probably avoid ever trying to follow a flowchart like this. What you could do instead is read these books, right? So these are recommended readings. I guess I said 6 books earlier. It's actually 8 books. These are books that I personally would recommend everybody who really wants to become a machine learning expert to purchase and read. There's Vladimir Vapnik's The Nature of Statistical Learning Theory, which talks about support vector machines. There's this classic, Due to Heart, and I guess Stork is the third author on pattern classification. It's a really nice introduction to machine learning and pattern recognition. There's this text here, the Hasty, Tibshirani, and Friedman book on elements in statistical learning. This has a great discussion of things like the bias variance trade-off, which we will be talking about in this class. That's a really critical problem. There's this old book by Chris Bishop. It's actually a book that came out in '96 on neural networks. It was during the previous wave of neural network excitement. And even today, this book it's a great read. He's a British guy, and he writes in a very British way, and so therefore it's really well written. And if you read this book, you'll be happy. And it's still up to date. I mean, a lot of the techniques they learn. I mean, a lot of it is just plain machine. Even though it's called neural networks, it's sort of not necessarily. It's not only applicable to neural networks. And he actually has another book out, Pattern Recognition and Machine Learning. This is more modern, has some more concepts, and it's also very good. There's Kevin Murphy's book, Machine Learning: A Probabilistic Approach. I like that book also because Kevin is a friend of mine, and we went to school together, and we've known each other for 30 years now. So you have to get that book, of course, because it's Kevin's. And then a more theoretical book is Shalif Schwartz and Shai Ben David's book on understanding machine learning. This is a great book if you really want to get down to the theoretical aspects of machine learning, some of the more mathematics behind why it works and how it works and when you should expect it to work and how many samples you need in order to get a certain error, and things like concentration bounds and concentration inequalities, which we'll briefly mention today. And then lastly, Introduction to the Theory of Neural Computation. And even though this is another old book on neural networks, but I still like this because it's somewhat mathematical, and it's actually it's coming from a physicist's perspective. So these authors are actually physicists who learned about neural networks and then wrote a book about it. So that's also another book. So I think if you were to get and read these books, you would be a master in machine learning. If you were to only get one of them, I would probably get. Oh, that's a hard question. Why did I ask that question? I don't know. All right, I'm not going to answer that question. If you were to only get 3 of them, I'd probably get these 3. If you were only to get one of them, I would get one of these 3. Okay. Okay. So what is machine learning? This is somewhat of a I guess a different perspective than what you'll probably hear elsewhere. So, the machine learning is really, in some sense, kind of an acknowledgement of a failure on the part of humanity. And what does that mean? It means that we as a species aren't smart enough to directly program computers to do complex tasks. We can't directly write a program to get a computer to recognize faces. And we can't directly write a program to get a computer to recognize speech. You're probably hearing a lot now that recently more and more what's happening is machine learning algorithms are coming out that are much better at detecting cancer than doctors, and these algorithms make many fewer mistakes, and they're more accurate, and they don't get tired, and they're cheaper. than doctors, right? So how did machine learning achieve this? Well, no one sat down and wrote, if there's a little red blotch on the left corner of the screen and there's a little black blotch on the right corner of the screen, and if there's a squiggly line here, then cancer, otherwise no cancer. So nobody wrote, and that's the traditional way that we program computers. Nobody wrote anything like that. We don't have the ability to do that as a species. We're not smart enough. But what we can do, machine learning is essentially sort of the production of algorithms that, rather than directly written by a human, are indirectly produced by a mathematical optimization procedure parameterized by data. And we're going to talk about this in a few different ways. So you might have heard, raise your hand actually if you've heard this. This is a famous saying. It's an old saying, I think that goes back to the 60s by David Wheeler, which says that all problems in computer science can be solved by another level of indirection. And that quote was written at the time early on in assembly and early maybe C programming, where basically says, okay, use a pointer rather than a direct reference or something. But in some sense, machine learning is another instance of this, because rather than write a program directly, what we're doing is we're writing a program that writes another program. And that secondary program that gets written by the first program that we write is the result of the machine learning system. And we could never achieve that second program if we were to write it directly. In fact, sometimes we write a program which writes another program which writes a third program. Sometimes it's doubly indirect. And it's that last end program, which is the machine learning program, the program produced by the machine learning process. And it's that last program, it's still a computer program, but it's that last program that is able to achieve these amazing things, like recognizing faces or recognizing speech. So that's a form of indirection in computer science. So, in some sense, rather than calling it artificial intelligence, I sometimes like to call it, rather than AI, I call it IA, for indirect algorithms. And that really is what's happening, indirect algorithms. And this has been, so far, proven over and over again to the best way to achieve these kind of grand challenge problems. And maybe it will also, there are companies like Coursera and so on and so forth, maybe this will also be a way we can address some of the other grand challenge and problems facing society, like poverty and energy and climate change and health. And we're beginning to address the problems in health, and hopefully we're beginning to address the problems in climate change using, maybe machine learning will be a big part of the solution, because we certainly can't write a program directly to fix climate change. So here, what do we mean? So traditional programming, let's clarify these points that I just made for a second. So, traditional computers were actually human. Like if you look at this picture here, where the word computer came from is that there would be people, during mostly wartime, and they'd be sitting there doing calculations by hand, needed for certain things, and they were basically people who would be doing long division, after long division problem after long division problem. They'd be sitting at a desk and doing basically simple arithmetic problems, long division, all day, and those were computers, right? And so I'm not going to read these comments. So, Donald Knuth, who's one of perhaps the most esteemed computer scientists, said a while back, let us change our traditional attitude to the construction of programs. Instead of imagining that our main task is to instruct a computer what to do, which is the traditional way of programming a computer, let us instead concentrate on explaining to human beings what we want the computer to do. So now machine learning isn't quite at that level. It's not quite at the level where you'd go for a walk with your laptop and say, so laptop, I'd like to solve this face recognition problem, and here's what it should do, and the laptop says, great, I'll get on it. It's not quite at that level, but it's a step towards this kind of quest, right? Where instead of a human sitting there programming directly a computer program which runs on a computer and does something that seems to be useful, instead of that model, we have, and this is this once level of indirection. So this is the idea that we have a human computer programmer which writes an algorithm, and that algorithm then takes in data, and data is a critical element of machine learning, right? Without data, I mean, in some sense, data science is a misnomer because there's no science without data. So what does it mean to be data science? But data science is really the science of essentially dealing with somehow data in a way, and machine learning essentially takes in data, runs the computer algorithm that was written directly by the computer, runs it on a computer, and then writes another program. So this program was written by this algorithm on this using this data, and this program, like if we zoom in a little bit, like this, here's an example of a MATLAB script. In fact, this is a very simple 6-line neural network program in MATLAB, something actually that I wrote back in 1994. But it's a very simple backpropagation algorithm. So you write something like that, but then the algorithm that it writes looks very different. It looks like a bunch of weights. I mean, you can plot it in certain ways, and here's an example of plotting receptive fields of a neural network. But what it really is just a bunch of real numbers, and it's not the case that you can sort of see while loops and variable names and arrays and structures and those sorts of things. The program that the computer writes is really just a series of numbers organized in a certain way. And when you run that program on another computer here, it does something seemingly intelligent. And this model, this indirect programming, is what machine learning is all about. And that's really all it's all about. And what we need to do is understand this. Like you in this class are going to be this person. You're going to be writing the program, which is going to be learned using this process. And the result of learning is going to be this program. And then you're going to run that learned program and see how well it works. Does that make sense? Okay, so now you know everything about machine learning. You don't have to spend any more time on it. And by the way, this is also AI. This is the method that has achieved, AI. This is the method that has led to all of these successes that you're seeing every day in the press about what AI and machine learning has done. It's indirect programming. So what does that entail? Well, I said that data is involved, right? So usually there's some big data collection effort. Data collection is really difficult, and it's really messy, and it's really error prone. And it's something that nobody likes to do, but everybody likes to have. Everybody loves to have data for their problem because it helps them to produce a machine-learned system. But still, you get some data, and maybe you get some data preprocessing tools. And one of the amazing things about Python is that so many of the data preprocessing tools that you might need are already built in for free in Python. And so you go through this stage where you sort of repeatedly preprocess the data, fix up the data, maybe do some feature extraction along the way, and make sure this is sort of the process that you sort of become. I like to say you become friends with your data. If you're an enemy of your data, it's not going to be nice to you, and you're not going to produce a good machine learning system. You have to get to know your data. You have to become intimate with it. Take it out for a beer or something, and get to know it, and then find good features. And after you've done that process, then you feed it to a learning algorithm of some sort. And there's lots of machine learning algorithms to test to. This is another iterative process, though, because the first thing you try will not work. And this is, by the way, one of the reasons why a lot of the programming assignments are difficult in this class, especially if you're familiar with the traditional model. So here's the traditional model of programming here. Debugging is relatively straightforward. You have a debugger, and you kind of know, maybe it dies with a seg fault or something if it's problematic, or it runs over memory or something like that. And there are these sort of traditional programmatic bugs that things like Purify and Lint and all these other sort of, programming tools can help you find. But when you're trying to debug a machine learning problem, you have all these parameters. And let's say, for example, all of the parameters, let's say for some reason they're supposed to be between the value in 0 and 1. So all of the parameters are valid, right? They're between the value in 0 and 1. But there was a major bug which led this program to not work, even though nothing seems to be a bug, and you're not running over memory, and you're not seg faulting or core dump or getting a floating point exception. So how do you debug such a thing? And this process here is the debugging process, or it's part of the debugging process, because not only do you need to find a model that works, you need to make sure that the model that you've tested hasn't been trained inappropriately, because you might move on. You might have found the perfect model for your problem, meaning it's fast, it's accurate, or at least has the potential to be accurate, but because of some bug, it doesn't work, and you move on and you don't consider it anymore, and you end up spending tens of thousands more dollars on trying to develop your machine learning system when the solution was right there. So developing a good practice of debugging the process of producing machine learning systems is really important. Okay, so after all that's done, then you've got that model, and then you deploy it, right? And then you've got an application, so you can ship it. You can say, okay, great, I've got my speech recognizer now that works on my Apple Watch or something, or whatever. There's the CES, the Consumer Electronics Show, that's happening today. In fact, I don't know, does anyone know about the CES show? There's a lot of consumer electronics that are happening every year. In early January, they have these things, and they show all of the latest tech devices. And every year over the past some number of years, AI and machine learning has had a greater and greater role in CES. It's a pretty major show with thousands of people. So you deploy it, and your product ends up at CES, and then everybody's happy, right? So how do we choose? What models do we choose? I mean, the ideal models are simple, are mathematically expressive, meaning that they're flexible. They're naturally suited to, one of the things is there's an amortization thing. Like if there's a model that works for one problem and also works for another problem, that's a benefit, because if you learn about the idiosyncrasies of one model and you become an expert in one type of model, and that model is very flexible and expressive and applies to many different problems, then that time you've invested in learning about this kind of model can be used for applying that model to something else. So ideally, we'd like models that are suited to a lot of different problems. And then lastly, of course, the model has to be practical. And what practical means is that it's efficient and scalable, and it can work on large data sets, right? Because data sets are very, very big. And if a model is just too computationally costly to learn and to train, then no matter how good the model is, if it takes 10 years to train, even if what you get at the end of 10 years is great, it's not going to be useful. Okay, object recognition. So that's the end of the introduction. So I usually like to try to pause and see if there are any questions at the end of each section. So does anybody have any questions at this point? This is all fairly high level. Does everybody understand everything we're saying? Raise your hand if everything I've said you've understood for the most part. Okay, raise your hand if you have a question. Okay, so those people who did not raise their hand when I said if you understood everything should have raised their hand if they have a question. So somebody, one of the things I like to do is not proceed until somebody asks one question. So let's just stand here awkwardly until somebody asks a question. Yep, question.
Are there applications that machine learning is not well suited to, like areas of data processing that's not
Well, yeah, I mean, it depends on the task. I mean, the first thing that comes to mind when you ask this question is something like sorting, right? Like, we kind of know how to sort numbers. Like, why, like you could imagine, training a machine learning system to take an unsorted array and map it to a sorted array, right? And so maybe it would kind of work, and maybe it would make mistakes, and eventually you'd learn something. But the question is, why would we want to use machine? We already have great solutions for it. These are problems that are very well understood. We have very efficient algorithms and very efficient implementations of those algorithms for sorting already. So why would we use machine learning for that? So there are like certain problems that you wouldn't use machine learning for because we already have better solutions for without machine learning. And then, learning, for any sort of data, like complicated real-world data processing task where data comes from real sensors, like it could be a temperature sensor or video camera or audio sensor or machine monitoring sensor or airplane or car. Like self-driving cars is a big topic these days, and one of the critical things about self-driving cars is that they have to be self-driving. So that would be great. That's obviously a great application for machine learning, because we need to make sure that it works and it's safe and everything. But that wasn't your question. You're asking things that are not good for machine learning. I mean, there's the arts. I mean, actually, even people are starting to use machine learning to do art. I'll have some examples of that. There was actually, I was just at a conference a few weeks ago, and there was someone who who I think of as she was a great artist, and she was using machine learning. But to me, my own personal opinion about that is that it wasn't that the machine learning was really doing the art. She was using machine learning kind of as a paintbrush, and she was doing the art using a new kind of paintbrush. And machine learning, if she's not actively involved in producing the art, it'd be just as good as a paintbrush sitting on a desk. You can't do anything without the human using it. So she was wielding machine learning to produce new kinds of art, and some of it was pretty good actually. I'll bring some in maybe next lecture. So is that using machine learning to produce art? I don't really know.
I've heard some of the stuff with like generating new classical music.
Yeah.
Machine learning data algorithms.
Yeah, people are doing those sorts of things, and in fact, there's a great website of not just classical music, but by the way, the classical music that usually I've heard generated by machine learning systems is pretty bad. But there's a machine learning system that generates an infinite amount of death metal, and it sounds really good. And you go there, and it's just it never ends. It's actually a YouTube page, and it's like this stream of death metal. It's always new. It's always never been done before, and it's infinitely long. If you don't do it now, but after the end of the class, go to search for infinite death metal machine learning, and you'll get it. And it's pretty funny. So some music is maybe more amenable to machine learning methods than others. Yeah, I mean it's hard to say because it's still a relatively new technology from the perspective of the history of humanity. I mean, the Industrial Revolution is hundreds of years old now at this point, and you could say, is there anything not suited to industry? Well, traditionally it's been art and music and maybe sort of interaction, personal interaction, like. At this point, I certainly wouldn't want to, like if you go out to a party or you go out to a bar or something, you wouldn't, like I said, you can go talk to your laptop, but it'd be much better to go out with your friends, right? So personal interaction. Yeah, I don't know. I don't know. That's a great question. I'll think more about that. Okay, so let's go on to object recognition and classification. By the way, thanks for asking that question. That was a great question. So this is an example. So, like, the asked question is a great question. So object recognition and object classification, what does that mean? By the way, like I said, we take a break after 2 hours. And oftentimes, at the end of 1 hour, we usually think that this is break time, but we're going to do another 50 minutes before we take a break. So, yes, we're masochists. All right, so our goal is to try to identify and make a distinction between objects that we find in the real world. Right? Now, it's something that humans find very easy to do. Like, we're trying to get computers to do things that humans find easy to do. Like, for example, does anyone not know what these objects are? Is anyone not using one of these objects right now? All right. You're not using one of them? You didn't raise your hand. Right, so we know what that is, right? And we also know what these are. And what's interesting about these pictures is that, there's a lot of variety of different tables, right? So these, tables, you can say, okay, a table has 4 legs. And so suppose you write an algorithm that says, okay, I'm going to write a table detector, and the first thing I'm going to look for is 4 legs. And then someone says, okay, well, here's a table that has only 1 leg. Or here's a table that kind of has 1 leg and 3 legs. Or this is another table. These are all tables, and we recognize them as tables. And there's a lot of variety of things that we see that we call tables, which make, for example, even though we find it trivial to identify tables, make writing a program directly hard to do. And what if we wanted to write a classifier? So we show it a picture, and the computer program is supposed to say, okay, either that's a chair or that's a table. Right? So sometimes it's not even obvious for humans what it is. Like, when is it like we have these kinds of things. So there you have something that you guys are using now. It's a chair and a table, right? Or here, this one over here. I mean, maybe that's a chair or maybe that's a table. If it's a chair, it's certainly not got a very comfortable back. But maybe it's a chair, maybe it's a table. I mean, here's something that's a chair, but it looks very different than most of the chairs that you might imagine as a chair. And here's something that maybe looks like a table, but maybe it's really more like a chair, or maybe like a cot or something else. And it gets even worse. Like, you have table chairs of various forms. Like, here's some designs for convertible tables and chairs, these sorts of things. And here's a strange, this one looks like more like a piece of art, which is a table. You can't really see it on the screen, but it's kind of like a chair here that's attached to a table there. So it's a table and a chair. So if you were to write a classifier, it's not necessarily always easy to know when it's a chair or when it's a table, or maybe when it's both, or when it's perhaps neither, because even though it has features of a table. And the problem becomes even more tricky. So this is the famous painting by Escher, who's a painter, drawer. And what's interesting about this is that it's sort of a slow morph between triangles and birds. So at what point, let's say you're trying to do triangle classification or triangle versus bird. You're trying to train a machine learning system or produce an algorithm to say either this is a triangle or this is a bird. But as you move along here, when does it switch from a triangle to a bird? Or if you're moving down here, when does it switch from a bird to a triangle? It's not clear, right? And in fact, what's interesting is that humans, like the boundary when it switches, it depends where you come from. So like if you're starting from birds, humans would say that, okay, it switches to triangles about there. But if you're moving up, you're saying it switches to birds maybe about there. So the point that you switch is different. Humans do this depending on where you're coming from. So it's not even clear that there's a well-defined answer to this question if humans disagree with it. Or here's another, there's lots of these great Escher paintings. Like what's foreground and what's background? Like you're trying to identify, a fish or a person or something. Somehow you need to separate the foreground from the background, but here both are foreground and background. So how do you deal with this kind of stuff? So the way we deal with it in machine learning, for the most part, is to use a representation of uncertainty, right? The key issue of these slides is that the world is a complicated place, right? We can't know everything, and we can't expect to know everything, and we can't expect to be certain about everything, and we should acknowledge and embrace our uncertainty, right? We should be willing to say when we're uncertain about something, and we should have some way of expressing how we're uncertain about something, and our algorithms should also have a way of expressing how it is uncertain about certain things. And we're going to be using, for the most part, for a representation of uncertainty, we're going to be using probability. Probability is nice. There are lots of different ways of representing uncertainty, which we're not going to get into because we don't have time. But for the most part, in machine learning and artificial intelligence, probability and probability theory and probability distributions has been traditionally the most successful way of representing uncertainty. And it has a very simple subjective working definition. So the probability of something is equal to the ratio of the number of times that thing happened divided by the total number of times anything happened. That's kind of a very simple frequentist definition of probability. And that works for a lot of things, for things that happen repeatedly. Like if we have a big data set, we want to say what's the probability of a tree, we would count the number of times that a tree exists in the image. Let's say it's an image data set. We'd count how many images there are and divide by the total number of images. And that's the probability of tree. So that works, but it doesn't work for certain things, like when we say, what's the probability that it's going to rain tomorrow? It's not like we can use a time machine and repeat tomorrow 1,000 times and count how many times it rained and how many times it didn't. But we still want to sort of use the notion of probability to express sort of a degree of certainty about something, or degree of belief about something. If we say the probability of raining tomorrow is 1, we're not really saying it in a frequentist sense. We're not saying, okay, well, if we repeat tomorrow many, many times, it's going to rain all the time. What we're saying is that we believe with complete certainty that it will rain tomorrow. Whereas if we say the probability of it raining tomorrow is 0.5, what we're doing is we're saying we don't know. We're saying it could rain, it might not. 0.5 is the least amount of certainty because we're saying we have no clue. It could either rain or couldn't. But then if we say the probability of it raining tomorrow is 0, then we're saying we're very certain again. We're saying we're certain it's not going to rain. So probability distributions not only are useful for these kind of frequentist definitions, but they're also useful for expressing degrees of belief about something and also for expressing uncertainty about events in the world. And we're going to be using it. So it's not perfect. It's got issues, probability, but we're going to be using it as our representation of certainty and uncertainty and belief. So what machine learning then does, like if we are developing a machine learning system that uses probabilities, what a machine learning algorithm is striving for is to identify the best probabilities for something in data using some sort of mathematical optimization. So for example, if we want to predict the weather tomorrow, what we'd look back, obviously we can't repeat the experiment tomorrow many times, but what we can do is go back in history and look at the weather conditions for as many different historical days as possible and try to identify conditions that are most similar to today and find from amongst all of those conditions that are similar today, how many of those historical tomorrows ended up with rain versus how many ended up with no rain. And that would be our probability. So it's not perfect, but it is something that kind of is a way of expressing our belief. We're using the history to sort of to sort of develop our beliefs about the future in a probabilistic way. And if it's the case that 50% of the time it rained and 50% of the time it didn't, then it says, okay, fine. We don't know. But on the other hand, it might be the case that we don't have enough data, or maybe there's the sensor on top of Mount Hood. Is Mount Hood the close mountain? I can't remember. Is anyone a mountain climber? Or let's say Mount Rainier. Let's say if we installed a sensor on top of Mount Rainier, suddenly we have a lot more information, and that will give us enough so that we can be certain, right? Because it might be the case that the reason why we're uncertain is that we don't have enough information, enough features, enough sensor information, sensor input to really know what's going on, and that happens a lot. Okay, so let's do a really simple example of machine learning in terms of coins, flipping coins. Everybody has coins, or at least everybody used to have coins. Now everybody has credit cards. But let's say we're flipping a series of n independent coins, and so this is a series of flips, B1 through Bn, and so each Bi is either H or T, heads or tails, right? And we're going to count the number of heads. So k is equal to the size of the set of indices I such that Bi is equal to H, right? So that's what that means. It's a count of the number of heads. Script D is our data set. We're going to be using script D a lot to represent data. Okay. So what we want to ask then is how true or how likely, and this is a really important word, likely, how likely is it that theta, theta is a number, right? Theta is a number that lives in the interval 0, 1. So it's a probability. How likely is it that theta is the probability of heads? So we can write this as this thing here. We can say, okay, the probability of the data given theta, which is saying theta, how likely does theta, a particular value of theta, render the data? And that there's an expression for that, right? It's equal to theta to the kth power, which is, k is the number of heads that we saw in the data, times 1 minus theta to the n minus kth power, which is the number of tails. So it's the probability of heads raised to the number of heads times the probability of tails raised to the number of tails. And that ends up being the likelihood of the data under hypothesis parameter theta. That's called a likelihood. And this is a critical thing. It's the likelihood of the data. It's not the probability of theta, it's the likelihood of theta. The probability of theta would be different. Right? So then how would we learn, we want to come up with a probability of heads for future coin flips, right? We want to learn a model. So we have a very simple probabilistic model. Theta is our parameter. We have this data set, and we want to learn. So what we could do is then say, okay, well, theta hat is the maximum likelihood estimate It's maximum likelihood estimates. And maximum likelihood estimate is MLE, right? MLE. So theta MLE is equal to taking the argmax of the probability of the data given theta. So what is the argmax? It's the argument that achieved the maximum. Is everybody familiar with argmax? Okay, we use argmax a lot. So if you're not familiar with this, you should be familiar with it. So the argmax of the probability of the data given the theta is the same as the argmax of the log, because log is a monotone function, and so log usually makes things a lot mathematically easier to optimize, and gives you the same answer because log is monotone, and the max before is the same as the max after the transformation of log. And so how do we do that? So if we were able to find that, that would be the theta that makes the data most probable. That's the MLE. And how do we actually find it? Well, we use calculus. We take the derivative of the log of the probability of the data given theta, set it as equal to 0, solve for theta, and what do we get? Something very satisfying. The relative frequency of heads. So just doing something as counting the number of heads and dividing by the total number of coin flips is a mathematically provably optimal machine learning technique for learning the probability of heads in a series of coin flips, right? That's the maximum. So that is essentially the idea of machine learning. So you might say, okay, well, what's this meta program you were talking about? Like, didn't you say you're going to program something? So obviously we're going to be solving tasks more complicated than predicting heads of a future coin, right? So the idea is like once we've got theta MLE, we can say, okay, I know what that coin is going to do much better than I knew before. And so next time somebody flips that coin, you can predict it better than random. I mean, better than random. If you were to predict 50-50, that would be random. Obviously, the other thing is that if theta happens to be 0.5, you won't be able to predict it, because then it's going to be completely unpredictable. But at the same time, if it's a biased coin, you're going to be able to predict the outcome of the coin with better accuracy than you would before you've done the learning. So that is a very simple form of what we can call machine learning. And maximum likelihood estimation is in fact a technique that's used a lot for many machine learning systems. And in fact, let's do another example. So let's see how close it is to the optimal solution. Like we can actually use sort of what are called concentration inequalities to do that. So let's say that D is again a sample of data. And now what we're doing is we're saying that theta MLE is a function of the data set that we've got, right? Because that whole process, that whole machine learning process is a function that maps from data using an algorithm to a parameter. And we represent that in this way. This itself is a random variable if D is it's also a random variable, because functions of random variables are also random variables. And in fact, in this particular case, it's a random function of it's a function of a random sample, right? So like, for example, going back to the coin, maybe I flip that coin 100 times once, and then I flip it 100 times again, or I flip it a third time 100 times. Every time I flip it 100 times, that's a random outcome. It's a random outcome consisting of 100 coin flips. And each time I take those 100 coin flips, I learn a theta. But each time I'm going to get a slightly different theta, because maybe, let's say it's a 60% heads coin. Maybe one time it's going to be 61, another time it's going to be 58, another time it's going to be 59, maybe the fourth time it's going to be exactly 60. Every time it's going to be different. And each time we're going to get a slightly different estimate, potentially. That's going to be itself a random variable. That estimate theta is going to be a random. And then we can then ask questions like here's something we might ask, which can be very useful. I'm not expecting you to fully understand this now, but what this is asking is, since this is a random variable, right? That's a random variable, as we just said. We can ask, what's the probability that this random variable deviates from the true optimal theta? We're taking the absolute value of this difference. What's the probability that it deviates from the optimal value theta star by more than epsilon? So there are certain mathematical methods, called concentration inequalities, and Hufting's inequality is one such concentration inequality that allows us to come up with an upper bound on the probability of this deviation. And what this is saying, what's interesting is that when you look at this upper bound, it's saying that this probability is less than this. This upper bound is an exponentially decreasing sequence in n. As n is the number of coin flips, right? So as we learn this model with ever increasing sizes of data, the probability of deviating from the truth, from the ground truth solution, is going to be decreasing exponentially. So, like if this is n, it's going this upper bound is going down very quickly. It's 2 times e to the negative 2n epsilon squared, right? That's decreasing fast. So what it means is that the power of more data is very powerful. And one of the reasons, one of the reasons we talked about is like, why is AI achieving such success these days? It's because of the power of what's called big data. Big data essentially just means there's a lot of data, and a heck of a lot of data, and there's a lot more information in bigger data. And because we have this is a simple example showing an exponential decrease in ability in the size of the data. When we have very large data sets, we can do crazy things like recognize faces or generate new faces or recognize speech or translate from English to German or do all sorts of things that we weren't able to do before we had these massive data sets that we could use for training. So the key point is that it gets good very quickly as n gets large. And that has led to what some people in the community say is there's no data like more data. Right? So that's kind of a pun. I don't know, does anyone know where that originally came from? There's no place like home or something? I don't know. But there's no data like more data. And what that really means is whenever you want to improve your method, get more data. If you're let's say you're working for some company, why are you here? Maybe your manager in whatever company you work for has asked you to take this class because they want you to go and figure out what all this machine learning stuff is about, right? And so you come back and you train some model and it's not working accurately enough. What this would say is, well, just get more data. And that'll help. Now, of course, there's a cost associated with more data. We don't want to indiscriminately just throw a ton of data on the problem, nor necessarily is any, we can't just duplicate the same data we've got, since there's no more information in the duplication of the data. So we have to be smart about how we get more data. But still, it is the case that there's no data like more data. Right, and this, right, so there's lots of other such methods. Right? I mean, there's not just, we talked about Hufting's inequality above, but there's lots of others, Markov's, Chebydev's, Chernov's, and Bennett-Bernstein, and so on and so forth. And there's machine learning paradigms. Pack learning is one of them, for example. We're not going to really get into it this quarter, but there's ways that you can actually mathematically analyze the learning process so we know precisely how many samples we need in order to achieve a given error. And so these are the kinds of things that often we think about. Okay, so let's now step back. I mean, first of all, let me pause for a second and see if there are any questions. Because we're going to leave the world of coins for a minute and go to the world of Gaussians. Are there any questions at this point? Okay, who has a question? Awkward silence. Question about coins? It can be about this stuff.
From the exponential decay,
Yep.
does that imply that optimization of AI will decrease eventually?
Well, this is showing. This is kind of like a measure of the badness, right? It's kind of like what's the probability of doing worse than epsilon? And it's saying that for any fixed epsilon, the probability of doing worse than epsilon is going down very fast. So this is saying that as you get more data, the probability of doing bad gets much smaller. And if the probability of doing badly is small, that means the probability of doing well for just this task. It's just this one task. I mean, this is not all machine learning problems, but one of the things we find out is that different machine learning techniques and different machine learning models require very different mathematical analysis methods. And one of the reasons why math is so important in the field of machine learning and AI is because in order to analyze when things work and how things work, you need to understand a lot of the mathematics behind it to do these kinds of bounds. This is the simple, like, this includes like that coin model that we just talked about, but it includes some other models as well. But yeah, but it basically, going into the future to answer your question, this actually means that if we get more data and we can we can afford to use it. We can either spend the time or we have the compute capacity to do it. That AI systems are going to get better. That's all that means. Which is, I guess, good news or bad news depending on how you look at it. Okay, so the next thing we're going to do is talk about multivariate Gaussians. So our data set, rather than being a sequence of coin flips, is now going to be a sequence of vectors. So x of I is really equal to a vector. And most vectors, vectors in this class are column vectors, right? So we have x of I 1, and x of I 2, x of I 3, and so on and so forth. And it's an m-dimensional space, so x of I m. And the idea is that x of ij is just a real number, right? So each one of these samples, this is a sequence of column vectors. So every single one of these guys is one column vector. And it's a series of n independent and identical m-dimensional, because this is an m-dimensional vector, real value samples, right, from a Gaussian distribution. And this is an example of a Gaussian distribution. It's a multivariate Gaussian. And you've probably seen like one-dimensional Gaussians before, and probably even multivariate Gaussians. So the one-dimensional Gaussian kind of looks like this, and this is the mean. Two-dimensional Gaussians might look like this, and these are contours of the Gaussian, and the mean is this point in the center, and the variance is how spread things out are, right? So like in the one-dimensional case, the variance is how wide the bell is, and in the two-dimensional case, you need more than one number to represent the variance. You need how wide it spread in the horizontal direction, how wide it spread in the vertical direction, and how the two horizontal and vertical directions covary with each other. Like if you increase one, does it increase the other, and vice versa? And so therefore, you need in 2 dimensions you need 3 parameters, and in n dimensions, you need n choose 2 parameters. We're in m-dimensional space. You need m choose 2 parameters. And that's represented by this matrix C. And this is the expression of a Gaussian, of a multivariate Gaussian density function. So one thing about the covariance is that it has to be a symmetric matrix. So that's why I say it's only like the off-diagonal elements. So that's why it's in m choose 2. And it's positive definite, which means it has some nice mathematical properties, meaning, like, for example, all its eigenvalues are positive, or we can represent it in this fashion. This is from linear algebra. And if we were to sample from it, it would look like this. Like, these are samples from a Gaussian, whose contour plots would probably look something like this. Hopefully you can see the different colors. The colors on the screen don't look nearly as good as they do on the laptop. I don't know if this is going to make things worse or better. Oh, that's bad. Okay, so is this something that you can, do you like this worse or better? Everyone will fall asleep. So should we keep it like this? Raise your hand if you want to keep it like this. Raise your hand if you want to go back to the old way. I don't know. Split down the middle. Well, how about this? So I'll switch it back on and off. So, like, for example, this is just like life, right? So anyway, so we'll keep it like this, and at the break we'll turn on the lights again. So so you can see the contours, and so a sample of this is a 2-dimensional Gaussian. So that means that m is equal to 2. Would look like that. And by the way, this can be done very simply. So here's an example of a Python program that this Python program generated this plot, and you will be learning you'll be doing a lot of Python. We just set the mean is 0, we set the covariance matrix, and we sample 1,000 samples, and then plot it. Okay, so what if it's the case that we just started from these points? So like this stuff here, these samples, like every single one of these x's is one dot. In this case, these are two-dimensional points, right? So every dot is the coordinate, right? In this two-dimensional coordinate plane. But now what we've got is we've got all these dots, and we want to learn. We want to learn what is the mean, and what is the covariance matrix. It's just like the coin problem, where we had a bunch of samples of coins, and we had that one parameter for the coin, which is the probability of heads, because we know the probability of tails is equal to 1 minus the probability of heads. We only had one parameter in the coin case. Here we've got a bunch of parameters. We have the mean, which is m-dimensional, and the covariance matrix, and there's, like I said, m choose 2 distinct values for this symmetric matrix. So we want to learn those things using maximum likelihood. So what we could do is then go ahead and do the same thing. It's express the likelihood. It's the probability of the data given the parameters. And the parameters in this case is the mean vector and the covariance matrix. And because if it's the log, and because things are independent, it's basically the sum of the log of the probability of the ith sample under the hypothesized mean and covariance. And that's what's known as it's the likelihood of the data given the parameters. And our learning strategy, our machine learning strategy, is to do maximum likelihood estimation, or MLE. Right? So MLE is maximum likelihood. Is we say, okay, well, here's the likelihood function here, and we want to maximize the likelihood. And so we find the argument that achieves the maximum of the likelihood by maximizing over mu and c, and then we get the resulting parameters after we do that maximization process. Now, how do we do that? Mathematics again. We take a derivative and set it equal to 0. In this case, we have to take the derivative with respect to the mean vector and set it equal to 0, and the derivative with respect to the covariance matrix and set it equal to 0. In this particular case, we have to do a little bit of extra work because there are constraints on the covariance matrix, but let's not worry about that right now. Let's just solve it in this particular way, and what we get is something that's extremely satisfying. The maximum likelihood estimate of the mean is just the sample mean. We take the vector average of all of the training data. So what that would mean is, if this is our data set here, it's basically saying find where the mean is, and you can even almost eyeball it. You can say, okay, that's where the mean is, right in the center. Right? And if we were to take the average of all of those points, it would put the average of all of those points about in the center. That is the maximum. That's the mathematically optimal maximum likelihood estimate of the mean parameter of a Gaussian, when it really is Gaussian. So every time you take an average, as you've probably done many times in your life, you are doing maximum likelihood estimation of a Gaussian. So you've done this before. If you want to find out your average monthly expenditures for, Irish whiskey bars in downtown Seattle, then you would be taking the average, the maximum likelihood estimate of a Gaussian, assuming that your average monthly expenditure, is a Gaussian sample, right? That would mean that sometimes it's negative, and maybe that actually makes sense because maybe sometimes your friends pay for it, and that would be like a negative expenditure, right? So anyway, that's the maximum likelihood estimate. Now the covariance is also equally intuitive. The maximum likelihood estimate of the covariance is taking the average of how much the sample deviates from the mean. I mean, it's kind of like, if you do the one-dimensional version, it really is intuitively, I think, kind of amazing, because it's just basically 1 over n, sum for I is equal to 1 to n of x of I minus mu squared. So it's the average of how much the sample deviates from the mean. And that's the variance. That's the MLE of the variance. So every time you compute the mean of something, and then you take the average of the squared difference from that of each sample to its mean, you're doing maximum likelihood estimation of the variance of a Gaussian. And then this is, all this is just the multivariate version of the same thing. So that's it. That's basically machine learning. What time is it now? So it's 7:39. Okay, so we're at the end of our Gaussian section, which means I have to ask another question. So let me turn on the lights. Okay, question. Yeah.
Why do we take the log?
The reason why we take the log, we don't actually have to take the log, but the log makes things a lot easier to deal with, just algebraically. Because like, think about like a good example is going back to these coin things. That's a very good question. And like, so we're trying to when we take the log of this thing, the k, which is in the exponent, goes down in front of the log, and then when you take the derivative, the log of theta becomes 1 over theta, and the log vanishes, and then we can solve for theta, and it suddenly we get a closed form solution to the maximum likelihood estimate. If we didn't take the log, it would be a closed form estimate would not be accessible. We wouldn't be able to do a closed form estimate. We could do some sort of complicated numerical optimization procedure, but we wouldn't be able to come up with a formula that gives us the maximum likelihood estimate. Now, taking the log versus not taking the log gives you the same solution, right? Because if you're trying to maximize something, that's the same as trying to maximize the log of it. Because the thing that maximizes something, if you take a monotone transformation of something that maximizes something, taking the log of it still has the same maximum. Because it preserves rank. Like log is a rank preserving transformation. It's a monotone, non-decreasing, rank preserving transformation. And so therefore, the log doesn't change the solution, but it does make a closed form analytical solution, namely this one, readily available. And generally speaking, that's almost always the case, it turns out. That taking the log helps. And we often do, even if taking the log doesn't help, we often do certain mathematical tricks that end up making our life easier mathematically without actually affecting the solution. That's something that we do a lot in machine learning. Because, after all, we want to get a solution. But that's a good question. And it turns out that that same log trick helps in the Gaussian case too. Like, how else are we going to get all this? I mean, look at this Gaussian expression. How are we going to get these parameters we care about outside of the exponent at the xp? Otherwise, it's stuck inside of the e function. And it's hard to deal with it, but once we take the log of it, suddenly they're right there, those parameters. And everything becomes a polynomial. Okay, any other questions on this section? I think we should do, because I said we'd take a break at 8. So it's 20 minutes to 8. So let's do one more section, and then we'll take a break. Okay. I know this is tough, right? Now, one of the things I always say is, like, you guys are probably getting tired and you want to take a break. You're not up here talking. You're not up here. It's a lot more tiring to not be sitting. Like, if you want to doze off and you want to think about the weather or something, I can't like doze off and think about the weather while I'm up here talking. Although actually there was one time I was so tired I fell asleep in my own class while I was lecturing. That happened only once in 20 years of lecturing. I hope it doesn't happen here. But if it does, it'll probably happen closer to 10. So let's do one more section, then we'll take a break at the end of associative memories. But before we do that, I just want to make sure that there are no other questions on the Gaussians or on the coin business. Maximum likelihood estimation is really what we're after. Yeah.
Is that T on the right side of the...
Yes, that's matrix. That's vector transpose, because that's basically this. This is the difference between two column vectors here, and this is taking the transpose of that vector. So if we were to look at this kind of pictorially, we'd have a column vector and then the transpose of a column vector. And when you multiply those two things together, it's matrix multiply. It just so happens to be a column vector times a row vector, and the solution would be a matrix. So every single term in this sum, this thing here, that's a what's called a rank 1 matrix. And then we're summing up a bunch of rank 1 matrices. in the scalar case, in the one-dimensional case, it doesn't matter. It's just we're just summing up a bunch of scalars. But each term here is just a scalar squared. But in the vector case, the analogy is to take these rank 1 updates, which is a vector times its transpose.
Professor, I have a question.
Yep.
So, whenever we talk about any distribution, I mean, Gaussian distribution is very prominent. In real life data, it can be really random, right?
Yes.
So why Gaussian? I mean, can
Um,
Gaussian model?
That's it. That's also a very good question. So, the question is why Gaussian? Like, why do we see Gaussians all the time? Well, the sort of somewhat cynical answer to that is that Gaussians are easy to deal with, and they're mathematically nice. I mean, look, we can do maximum likelihood estimation trivially, right? And computing the mean, computing the variance is really easy. And after all, we compute means all the time. And one reason we do the Gaussian is to understand what it means to compute a mean. 'Cause like when you compute this kind of mean, you're kind of maybe you're making the assumption that it is Gaussian. And maybe that shouldn't be the assumption. Maybe computing the mean should be based on some other distribution. But the real answer, the non-cynical answer, is that Gaussians actually turn out to occur in nature quite frequently. And they're kind of amazing how often they're appropriate. And even if they're not exactly Gaussian, they're almost Gaussian. And there's also something called the central limit theorem, which is that if you take certain constructs, like certain sums of random variables, it converges to Gaussians. I mean, no matter what the original random variable is. I mean, if you take certain sums and if you take the difference between a random variable and its mean and you sum up these things, then you get essentially a Gaussian. And then the third thing is that even when Gaussians are not perfect, oftentimes Gaussians are good enough, because we don't, when we're doing machine learning, we don't have to always be 100% correct. There's a certain tolerance of inaccuracy that we're willing to accept. And then the last thing is that Gaussians are often the stepping stone towards more complex distributions, like mixtures of Gaussians. So like maybe it's not, Gaussian is always a unimodal distribution. There's one point, which is where the mean is. But what if you have a distribution that's bimodal, where you have two modes that look something like this? Maybe you've got a peak there, and then a peak there, and then a peak there, right? That could easily be represented by a mixture of 3 Gaussians. And it's a sum of 3 Gaussians. And there are ways of learning mixtures of Gaussians relatively easily using maximum likelihood estimation-like methods. And that's the EM algorithm, which you might have heard of, the expectation maximization algorithm, which we will be covering. And we're going to drive the EM algorithm in this class. So yeah, they're not always useful. They're not always perfect, but they're often very useful. And often, the other thing is that they're often things like logistic regression. Like one of the simple classifiers that we're going to talk about, which is kind of like a one-layer neural network, by the way. Logistic regression turns out to just be the posterior probability under a Gaussian distribution. So it's kind of like when you think about a neural network, you can almost think of it that each layer is kind of like a Gaussian in some sense, and you have many layers, and the whole thing is no longer Gaussian. But if you take multiple layers of logistical regression, you're kind of like composing Gaussians with Gaussians with Gaussians. And so they just come up all the time. They're just very natural. So I think there's lots of reasons. And Gaussians are very rich mathematically. They have all sorts of other properties that were like things like the Schur complement and conditional Gaussians and those sorts of things, which we're not going to really get a chance to get too much into in this class. But there are other reasons as well. So, yep.
Are we using log-based 10 and log-based 2?
In this case, we're using log-based E, right? Because in the case of, because when we have the Gaussian, we're using the exp function, so we're using log-based E. But usually, I'll specify. So if we're not in this class, if we're not specifying which log we're using, is log-based E, so a natural logarithm. But if we're using base 10 or base 2, I'll mention it. Usually in information theory, when we're talking about things like entropy, we use log base 2. Okay, associative memories. Let's spend 10 minutes on associative memories. So hopefully people are somewhat familiar with Pavlov's dog. Pavlov was a famous behavioral psychologist from, I don't want to give the date, 1920s, something like that. So what he learned, Pavlov, was, by observational study that whenever he would show a dog a bowl of dog food, the dog would get very excited because the dog would realize that they're about to get fed and would start salivating, right? And get very excited and food, But if you'd ring a bell, the dog was not particularly interested in the bell. He was kind of bored. But if you repeatedly, simultaneously showed the dog and allowed the dog to eat while ringing a bell, the dog kind of learns to associate the sound of the bell with food, so that in the future, if you were to ring just the bell without the food, the dog would start salivating. So the dog learned to associate the act of ringing a bell with food. That's what we mean by association, right? And so the dog, in some sense, is learning an associative memory. That the input to the associative memory is the bell, the output is the behavior of the dog salivating. So it turns out machine learning is very similar to associative memories. So there's various different forms of associative memory. There's auto-associative memory or heteroassociative memory. But in general, what we mean by an associative memory is kind of something that associates something with something else. It's like here, we have, we have X as an input, and X comes from some alphabet, script X, and Y is an output. And we have an associator, H, which associates the input to an output. You can think of it H as a function or as a mapping, but in general, it's really like an associator. It associates inputs to outputs. And so if H was the dog, then X could be either food or bell, and Y could either be salivation behavior or no reaction. And what the dog has learned to do, the dog's H function changed in response to training, right? In response to hearing and seeing the food simultaneously, the dog learned to associate a bell with a particular behavior. Now, there's lots of ways of achieving associative memory. I mean, those folks who are familiar with computing systems might say, well, hey, I can do this. I can do an associative memory with a hash table, or even with an array, right? I can associate an index into an array to the contents of that array cell, or I can use a hash table, or I can use some sort of map-based data structure like a red-black tree of some sort, which is what I think Python uses for lists or dictionaries. But we want something that's in some sense more powerful than these kind of fixed data structures, or they may not even be fixed. These kind of like explicit data structures. What we want is something that can deal with the following: that we've got X and Y, which is very, very large. So like it might be, the set of possible inputs might be exponentially big. Like imagine how many possible 20 megapixel images are there? I mean, 20 megapixels isn't even that big by modern standards. I mean, there are cameras coming out now with 63 megapixel images. So if you take a 20 megapixel image, and each pixel has 3 color channels, and each color channel, let's say 8 bits. I mean, even in a 20 megapixel, even in a 1 megapixel image, there are more possible images that can display than there are atoms in the known universe. Right? I mean, on your phone, like the set of possible images that could potentially be displayed on your phone is greater than the number of atoms in the known universe, in all 13 billion light years of the universe that we know. And that's kind of phenomenal, because that the representational capacity of just that one image is just ridiculously big. So the set of possible images is big. And we want to learn from this very, very big space to the output, which is whose face it is. Right? And that already is a very big face. And we only have sample associations. So the training data is a set of example associations. Like X could be a picture of Mary, and Y would be the name Mary. And X2 could be the picture of John, and Y2 would be a picture, the name John. And X3 could be a picture of Sumit, and YPC could be the name Sumit, and so on and so forth. So like these are all represented in data, but somehow you need to be able to generalize, to be able to say, okay, well, now I've got these example associations. How do I learn to associate between pairs that I've never seen before? So if I have a picture of Mary that was never represented in my training data, I still want to be able to say it was Mary. A hash table can't do that. If you take a picture of Mary that's not in the hash table, you look up and it would say, sorry, Mary's not in the hash table. because it's a different picture. You never saw that picture before. So what that means is we want to build an associative memory that works even outside of the training data, or even for X's, for inputs that are not one of the inputs in the training data, which is what this represents over here. So why do we want to do this? Like, why not just, get all of the inputs? I mean, like we would do in a hash table. Well, one reason is because X is just so big. Like we can't take all the possible pictures of Mary, right? We want to be able to generalize. We want to be able to sort of use aspects of Mary or Bob or whoever that we are trying to recognize faces of, so that we recognize them when they have different facial expressions, different times of day, different moods, different lighting conditions, different everything else, different air, clarity, different resolutions, whether we're zoomed in or zoomed out. All of those sorts of things shouldn't affect our model, and it's impossible to get all of the different possible variations of the same person. X in general might be, either just infinitely or effectively infinitely large. Like, for example, the number of images on your phone that your phone could represent is, for all intents and purposes, it's infinite, right? Might as well be infinite. It doesn't change much. So what machine learning's goal is to try to deal with this. It's try to solve a very difficult sounding problem, which is basically, given a data set D of these pairs, and this is the goal of machine learning, to produce a working associative memory. To, given a data set D, produce some program, to produce the associative memory that generalizes and works well on samples that it's never seen before. So it should recognize speech utterances that it's never heard before. And it should drive a car on roads it's never been on before. And it should fly an airplane in turbulent conditions that it's never been in before. All of those sorts of things are ideas of the ideas of generalization. Or it should detect cancers in cancer screening images that it's never detected before. And there's lots of things that can go wrong. Like, there can be a variety of variation. We talked about variation in face recognition. There can be noise. The sensor could be corrupted. The data could be corrupted, or there could be an adversary who's deliberately trying to sabotage your system, and you still want to be robust to adversarial conditions too. Hackers trying to break your system. And simultaneously, we want to do this efficiently. We want to make it feasible. We don't want to spend 100 years training our system. And we want to understand it mathematically. We want to explain it. You get recommended a movie on Netflix, and you ask Netflix, why did you recommend that movie? That's kind of a weird movie to recommend to me. Why the heck did it recommend that? And if it says, sorry, that's what the neural network says. You watched this, and the neural network came up with this, and you want to have some idea why. So understanding why it does what it does, and explaining why it does what it does is necessary for human interaction. Because whenever you have a friend, and your friend recommends that you should see there's two possible movies you could choose: either The Irishman, or Avengers Endgame. Right, and which of these two movies? And if your friend says you should choose Endgame because you wouldn't like these Martin Scorsese movies are too old-fashioned, or something, then you say, well, why do you think that? Why do you think I wouldn't like these classic old-fashioned style movies with gangsters and so you can ask it, and then you want to be able to do the same of any machine learning system. So what it boils down to then is this idea of associative memory, right? We want to find a good associative memory that can do the mapping or the association. And sometimes we have a collection of possible mappings we choose from. Like, script H might be what's sometimes called a hypothesis class of possible associators. But more frequently, we have effectively an infinite-sized class parameterized by a bunch of parameters, theta. And theta isn't just a single number. Theta might be 100 million numbers. And we want to find the value of this 100 million long vector that gives us an associative memory that works well in the future. and leads to a good H theta. So there's many ways of doing it, and in some sense that's what we're going to be studying a lot. We've already kind of done it a little bit. I mean, in the maximum likelihood estimation case, we did MLE for coins and for Gaussians, but that's not an associative memory. That just learns the probability of a coin, or learns the parameters of a Gaussian. Here we're trying to map from X to Y, which is a little bit different, right? We're trying to find a mapping. And we want to do this efficiently, like I said. Okay, so that's what we mean by associative memory. Now, the term associative memory, I should mention, you don't hear that term used that often these days in machine learning, and it was used a lot in the 70s and 80s in the early neural network world. But I think it really does get at essentially what we're trying to do. We're trying to learn something that associates inputs to outputs, even for inputs that we've never seen before, and even when the input could be from a space which is potentially enormous. And it should do something intelligent no matter what you give it. Like imagine, like you could spend your phone looking at images on your phone, let's say 120 frames per second, and every frame would be a completely different image. And if you spent your entire life looking at your phone's video at a high frame rate, you wouldn't even scratch the surface of the number of possible images that your phone can represent. So somehow humans can do it. Like humans, this is actually, so I have two kids, right? And so they, I remember once when my oldest son was, I think he was about 1.5 years old, and we were walking along a street, and there was this wire structure, this really bizarre looking wire structure. And he looked at it and he said, "Cat!" And it was in fact a cat, but it was this really bizarre looking wire structure that had kind of weird metal ears and weird metal whiskers, and it barely looked like a cat. And at that point in his life, he'd seen maybe 2 or 3 cats. And he saw this wire structure and he knew it was a cat. So how is it that humans can generalize so rapidly from seeing only a very small number of cats to looking at a crazy artistic wire structured cat? And he noticed it was a cat even before I did. And he's only seen a few cats in his life. So that's kind of what we're trying to get machines to do. We're trying to get, humans are have remarkable associative memories. So, okay, with that, I think it's now officially break time. But before we break, let's ask our compulsory question. So we can't go and break until somebody asks a question. So whoever asked the question, everybody else in your class will thank you. So go ahead and ask a question. Yep.
So for the parameterized versus just possible associators, is it sort of, could you do just try and create different associators versus ones that are parameterized? Is there a trade-off for that, or is just one better than the other?
They're kind of, sometimes this is nicer from a perspective of analysis. Like it might be the case that you can actually talk about how big that is, and you can represent its volume, and then you can actually detect how like as you're learning, you can sort of eliminate hypotheses as being impossible. And so there's certain useful tricks and techniques and sometimes mathematical analysis methods that can be used to help you understand how quickly you're learning based on how far that hypothesis class has reduced, meaning you're like any hypothesis that's not consistent with the data you've seen so far, you toss away. And so H gets smaller and smaller and smaller and smaller until hopefully you're left with one and only one, and that becomes the solution. And hopefully you're not left with 0, right? This thing here is, it might be the case that there's no it's sort of different. Like neural networks fit more in this model where you have or logistic regression, or the kinds of models that we're going to be learning about in this class, where effectively the space is infinitely big. And even though the space is infinitely big, there may not be any one model that perfectly fits the data, nor would you want a model that perfectly fits the data. But you want one model that sort of is best on average, in the sense it's got the lowest error. It still has error, but it's the lowest error. and oftentimes that's good. So usually they're used for different purposes. This, I should actually mention that, like, there's one paradigm of learning called active learning, and this hypothesis class is used a lot in that kind of paradigm for understanding when active learning works. We'll talk about paradigms of learning in a future lecture. Okay, but that's a good question. All right, so let's take a break, about 5 minutes, and another question. Sorry, say again.
When you relate the X and capital R to the Pavlov's dog example, how can we relate that?
So I'm not hearing the question. Do you want to come up? I didn't realize there was another question.
So when we relate this smaller X and the capital R to the Pavlov's dog example, I understood this capital X and Y and H. X is kind of, I'm trying to relate with that example actually. So
Okay,
how
so-
can we
so-
practically explain this X and R?
Okay, so this is a what we're saying down here is that often X is an m-dimensional real valued vector, and so this is the set of all possible m-dimensional real valued vectors, and we're saying that X is one of the m-dimensional real valued vectors. Right? That means that X is in this set. So this is kind of like set theoretic notation.
So here we are telling about what kind of features here.
Right. But like we're saying that often it's the case that X is a real valued vector, but it doesn't have to be. X could be a binary vector, or X could be an integer valued vector, or X could be a set of strings. X could be all sorts of stuff. But we usually, oftentimes what we'll do is we'll treat it as or we'll transform it into a real valued vector. And that's important because that's the feature extraction process. Let me just pause this. So we're getting started for the second half of the class. We've got an hour and 45 minutes to go. So is everybody ready? Okay, is everybody refreshed and recharged and? Siri got triggered. So there's a failure in machine learning. Like sometimes I'm just talking and Siri turns on. So okay, so we talked about associative memory. So like here's a very simple example of an associative memory, where what we're trying to do is we're trying to learn to associate the living area of a home to its price in thousands. And so we would gather, for example, a big table. This is a very simple example. So X would be here and Y is there, and both X and Y are just scalars, which is just a single number, and we're trying to associate from this to this. By the way, this is an example taken from Andrew Ng's class, who's somebody else I went to school with back in the day, at the same time as Kevin Murphy. So we can, for example, like plot this data. We can say, okay, well let's look at we have living area in square feet on the x-axis, and price of the home on the y-axis, and what we might do to try to learn to associate from x to y is fit a model, and a model might be something very simple like a linear model, which would just be a line going through that, and that would be our model. Now it doesn't fit the data perfectly, but it kind of fits it roughly, and it correlates. It gives you the same sort of correlation if you were to compute the correlation on that data. Or you might say that a linear model is not good because no matter what linear model you choose, if you choose this one, or if you choose this one, or whatever one you choose, it's never going to always be correct with respect to the data. And if you believe that these errors, right, these are errors with respect to your training data. This is your training data in this table, are big enough, then you would say maybe I need to not use a linear model. Maybe I need to use a model that has some curves to it, like a model that does something like this, right? And that would be a nonlinear model, and you'd fit that. And the nonlinear model can be as complex as you want. It's like you could have something that does something a lot more complex and fits the data much better. But there's reasons why you wouldn't want to do that either. So one thing you might want to do, even before you go on and use a more complicated model, is use more inputs. Because maybe maybe just living area by itself, like rather than going to a complicated nonlinear model, you might say, well, wait a second, living area by itself is just not enough to do a good job at predicting, the house price. Maybe it's something other than living area, like for example, also knowing the number of bedrooms of the house would be more accurate. And so here now we have the same table of data, but we've got living area, we also have number of bedrooms, and we have the same output. So in this particular case, we have X is this guy, and this is Y. X is now two-dimensional, not one-dimensional. And it's potentially better, right? Because you've got more information. You have more that you can use to associate between X and Y. And you can always decide to throw away the number of bedrooms if you want, but chances are that that's not going to be a worthwhile thing to do. You want to keep the extra information if you've got it. So it's higher information. It's higher dimensional information. So you have more dimensions. But there's a trade-off here, right? Because you could then keep adding more and more information. So like you could say there's the living area, there's the number of bedrooms, which is maybe the yard space, which is what does it have a basement, which is the number of floors does it have. Maybe is it on a hill or not, or is it in a flat? Is it in a flood-prone area, or is it a non-flood-prone area? What city is it in? What's the zip code? There's all sorts of other things you could use that would help you to predict the house price. So more inputs means potentially more information, and which means potentially more information for accurate association. So that's the good. The bad, however, is that you're now in a higher dimensional space. And when you're in a higher dimensional space, in order to do an accurate association, you need more data. So, like for example, earlier on, like maybe here, this is maybe, I don't know, like 30 points or something, maybe 30 or 40 points. In one dimension or two dimensions, 30 or 40 points is enough to get a sense of, maybe a line would be good enough, or maybe a slightly curved nonlinear function would be good enough. But if you're in a very high dimensional space, you're going to need many more than just 30 training points to actually do a good job associating. Because space is very different in high dimensions. And we're going to do some, in the next couple of lectures, we're going to try to understand the mathematics of high dimensional spaces. And you're going to see some really, really crazy, bizarre things happen in high dimensions. Like we're going to talk about high dimensional apples. And high dimensional apples are all peel and no core. And you're going to say, well, how does that make sense? And we're going to see that we're going to study an apple. We're going to say a high dimensional apple. We're going to say that the peel is only epsilon thick, but that's going to be all. Even though it's only epsilon thick, as the dimensions go up, all of the apple is going to be the peel. By the way, it's the same as for high dimensional oranges too, or high dimensional mangoes. They're all skin, or all pith. So the problem is things are different in high dimensions, and so we can't always use. We're kind of limited to thinking about low dimensional spaces, extremely low dimensional spaces, namely 1, 2, or 3 dimensions. And we can barely imagine what a 4-dimensional space is like. We can't point in the fourth dimensions. We can think maybe of time as a fourth dimension. But when you're talking about 1,000-dimensional spaces, or 100,000-dimensional spaces, or million-dimensional spaces, all our intuition is completely wrong, because things are very different. But what we can do is we can use mathematics. We can to study certain properties, the properties of certain things that exist in high dimensions, and we will do that. But this is basically the idea of the curse of dimensionality. This is a fundamental problem. Is that as the dimensionality gets higher, things become difficult, because the properties and geometry sort of behaves differently from what our intuition says it should. And also, in order to sort of populate the space as a consequence of the way that high dimensional spaces behave differently, in order to populate this space with points in a way so that we can learn, we need an exponentially larger number of points as the dimension goes higher in order to properly populate things. So somehow it's working though, right? Because we're working in high dimensional space. Like these images are, megapixel images. That's pretty high dimension. 1 million dimensional space in a megapixel image. Each pixel is a dimension. Or maybe each pixel is 3-dimensional because you have 3 color channels in an image, RGB. So a megapixel image is really like a 3 million dimensional space. And somehow we're able to work in that space. We can produce machine learning systems that do a good job recognizing images or generating images in high dimensional spaces. But we only do that by acknowledging how things are different and by acknowledging and understanding the cursive dimensionality. Yeah, question?
In some of the other courses I've taken, often when we do image processing, video processing, they grayscale the image. Is that to reduce does that potentially reduce this dimensionality?
There's a lot of reasons for grayscaling an image. Sometimes of which it's sort of useful for doing certain noise reduction algorithms in grayscale. Sometimes it's nicer to visualize things and doing certain like sharpening and those sorts of things that people do in computer vision and image processing. I don't think that you would, for example, if you were to do a pattern classifier, the first thing you would do is do grayscale, because let's say you're trying to recognize cars or objects like trees. Right? If you don't know if a big blob is green, I mean, green is a big clue that would tell you that it's a tree and not something else. Now you could still do it, but you're throwing away color, which is a useful piece of information to help you do object recognition. So if you were to do that grayscale thing, you would probably do worse in terms of your accuracy. So that's sort of going backwards, right? So that's with regard to this trade-off. The more inputs, the more information. So if you go from grayscale to RGB, you've got more inputs, you've got more information. And color is certainly critical for image processing, computer vision. Face recognition is critical. Color, you need color. We see in color. Color has a lot of information in it. But at the same time, there are other. I know that, like for example, I mean, if you do like Lightroom, if you're into photography and you use like Adobe Lightroom, there's certain photo editing software like Photoshop and Lightroom. Sometimes it's useful to visualize it in black and white for doing various like I said, sharpening steps and so on and so forth. Okay, so cursive dimensionality. We will be revisiting this. Statistical parameter estimation is essentially one way of essentially achieving this. So what we're going to start with is we start with our data sets, and the data set consists of a set of n pairs of samples. So it's xi and yi. The reason why, by the way, we're using this superscript here, we're going to try to use notation as consistently as possible throughout the class. The reason why we're using the superscript is we can now talk about things like x of I of j, right? And so it's like the jth element of the ith vector. Or we could write it this way. We can write x of I sub j, which would be the jth element of the ith vector. So we have now pairs which are called training pairs, right? X, Y. We're trying to associate from X to Y. And let's assume that these are drawn from some probability distribution. And we're not necessarily aware of precisely what the distribution is, but oftentimes what you do in statistical parameter estimation is you make the assumption that there is some probability distribution that the training data comes from. And that distribution is P of xy. And in this case, let's say that x of I is m-dimensional column vectors of features, and yi is a scalar, right? And the goal is to find this associative memory, find the classifier, find the thing that maps from x to y that minimizes the error. So how do we do this? This is a very classic sort of supervised machine learning problem. And this is mostly, we're going to talk about classification and regression. This is mostly regression because in this particular form, y is a real valued scalar rather than like a Boolean or an integer. So the error, so this is now a classifier, right? It's a regressor. It basically says, I'm a function that's parameterized by theta that takes x of I as the input, and I produce something that's supposed to be close to y, to the corresponding y, for each one of these pairs. And taking this difference is the error, is how bad you're doing. And if the difference is equal to 0, then you've done perfectly. You've exactly represented y. And the extent to which it's not y corresponds to the error. And you can take the squared error. If this is a scalar, then we can square it. And we can take the expected value of the squared error, and since this is a distribution, we can say, okay, what's the expected value? What's the average error of our classifier? And you can think of this as like something, this is kind of a thing that you'd want to be small, right? It's saying, on average, over the probability distribution of x and y, I want my error to be small. And if it's the case that, I mean, let's just zoom in on this for a minute, because I think this is really important to understand. If it's the case that there are regions of x and y that never happen, because the probability of certain x and y is 0, then we don't care about the error there, because it essentially multiplies it by 0, right? So this is the definition of the expected value over here. So we're taking the integral with respect to x and y of the probability of x and y and the squared error. So if there are regions of x and y that it gets 0 probability, the error doesn't matter. The error only matters in regions where there's non-zero probability. In fact, the error matters most where there's high probability, and the error matters least where there's low probability. And so you might then say the idea of machine learning is to find the theta that minimizes the expected error. And finding the theta that minimizes the expected error involves trade-offs. You might say, oh, the probability is low. Like, think about xy space. There might be this big chunk of xy space where the probability is close to 0. And the machine learning system might say, hey, the probability of seeing something there is so small, I'm going to allow the error to be big in this region for the benefit of having this other region, which has high probability, to have low error. Right? Because I want the error to be low where I'm likely to see stuff, where stuff is likely to happen. I don't care if the error is big where it's impossible or it's extremely improbable to see stuff. Yeah, question.
Is that the probability that XY appeared in the training data?
Well, here where the training data is our indirect surrogate access to P of xy. Right? So this training data was sampled presumably from this distribution. But right now what we're doing is we're saying, if we had this distribution, that's even better than the training data, right? Because we actually have the truth. We have ground truth probability distribution. We don't in real life ever have access to P of x comma y. But what we do have access to is a training data set which at least gives us some information about P of x, y. Because if there's regions of the space, I mean, even in the Gaussian case, like if we see lots of points over here and very few points over here, and the sample size is large, the probability in this region is going to be much larger than the probability is going to be over here. So we're going to use samples to represent this. But for right now, for this discussion, let's just think about it as this integral, right? So we just have access to everything. And the idea of training, machine learning then is to say, find the theta that minimizes the average error. So this is our first, sort of loss function, right? Now, with a little bit of, algebra, we can say, okay, conditional probability, we can represent it in this way. It's the integral over P of x, the integral of error of P of y given x. And theta is a vector of parameters, and so on and so forth. So all we need to do is figure out an optimization procedure, a mathematical optimization, to minimize theta. So we can actually do that. I mean, just mathematically, we can say, if we take the derivatives, set the derivatives equal to 0, and solve for h of theta, we get a solution which is this, which is that the best predictor for a given x is taking the expected value of y under the distribution of P of y given x, which is defined as this quantity here, E of y given x. That's the best associator. So it's kind of like saying, for every given x, that x imparts a distribution over y. Okay, now y is a random variable, right? So for any given x, there might not be one right answer for y, right? But what's the best y to choose? Well, for that x, choose the mean of the y. And that's the best you can do. If you have to predict one answer, predict the mean. This is the conditional mean. And so that's it. And so that very simply gives you the optimal solution, optimal from the perspective of minimizing this expected error. And that is, again, another machine learning method. Now, is it practical? You're asking, well, we don't have access to keep x comma y, right? That's exactly right. We don't actually have access to it. We only have a training set. Not to mention, even if we had a training set, how are we going to compute this thing? How are we going to compute e of y given x? Like this is not even a tractable thing necessarily to compute. So, but in some sense, we have a mathematical expression of our ideal. This is the, in some sense, light speed version of statistical parameter estimation, meaning that this is what we would ideally like to do if we could do exactly what the mathematics says that we're supposed to do. But what we actually do is something that tries to approximate this as best as possible. But does the intuition about this being a machine learning method, this being essentially a strategy to achieve a theta, and achieving this, like we haven't gone into the details of how we take the derivatives, and there's a bunch of algebra, maybe calculus associated with taking derivatives and setting it equals 0. But that is somewhat mundane relative to the core thing we want to impart right now to you all, which is that this is essentially a form of machine learning. And in fact, it's a form of supervised learning. Yeah.
Can't we pose this as an optimization problem for P of xy? Say we parameterize P of x comma y using a variable theta, and we get a probability distribution, and given the new x, we find the y which has the most maximum probability, and we get the outcome. So can't.
Yeah, I mean that's right. I mean, but you know, doing you know, in practice, I mean, it may be that, suppose it's the case that we go ahead and do what you just said, and we learn Py given x, right? And then every time an x comes along, we compute this interval, right, this expected value. But what if it's the case that we can show mathematically that this happens to be just some very simple function of x? Like, what if a neural network actually does a pretty good job, or does an exact job? What if it's the case that if we were to represent this expected value mathematically, it ends up being a neural network, or it ends up being a decision tree, or it ends up being something that we know. So why should we go through the work of estimating this conditional distribution? That's more, you know, generally this is sort of the Occam's razor principle. Or don't solve a problem using more complex tools than you need to solve the problem, if you can solve it something using more simply. And if we can actually have a parameterized model, like we talked about, you know, this thing at the beginning of class that showed all these different models. Like, there was a question. Wait, let me just. There is some way of being able to zip around these slides really quickly. Like we talked about this guy here, right? This picture, and models and representations. There's lots of different ways of possibly representing the expected value of y given x. It could be a naive Bayes classifier, or it could be a k-nearest neighbor, or it could be a decision tree, or it could be a neural network, or it could be a Savoy vector machine. There's lots of different ways, and those are much more direct ways of getting the answer than having to actually estimate the probability distribution, which might involve, you know, millions more parameters than it would need to just represent it directly. Not to mention computation. Like every time we get an x, we have to compute that interval. What if it's just a neural network, which is just a bunch of matrix multiplies? It's a lot easier. And still not necessarily mathematically incorrect, if we can show that that integral has a functional form corresponding to a Swartz vector machine or a neural network. But yes, mathematically you could do that. Now let's see, I think we were here. Okay, so let's do this a little bit more, in a little bit more detail. We're going to do it in the context of linear least squares and linear regression. So that's kind of like what we've been talking about. In the case of linear regression, the model actually looks like this. So we're assuming, you know, x is a vector, which is it's an m-dimensional vector, x1, x2, up to x of m. And theta is also a vector. Theta 1, theta 2, of the same dimensions as x. And our model, it's not a neural network, it's not a support vector machine, it's something simpler, just a simple dot product. It's a linear model. And in this case, theta consists of the regression coefficients, and in which case our hypothesized y is just this dot product. You see why this is a dot product, right? It's a vector vector times vector. I'll just in case, I'll just write this down. So it's basically the sum for j is equal to 1 to m of theta j times x of j. Just a dot product. Inner product it's also called. Okay, so we've got these parameters theta, and then here's now, it's no longer the case that we have p of x comma y, but we have our training data. So we can write an objective. This is a training objective. So the word objective is used a lot in machine learning. It's an objective for what? An objective is sort of the function on the parameters that is the thing we're trying to minimize. So we're trying to, in this particular case, find the theta that makes j of theta as small as possible. Now sometimes you want to maximize, sometimes you want to minimize. It shouldn't matter that much conceptually. In this particular case, you do need to know whether you want to minimize or maximize. Here you want to minimize. Why do we want to minimize? Because we're taking the sum of the squared error. And when you're measuring error, obviously you want to minimize. You want to minimize it. If you're measuring something else, like likelihood, you want to maximize it. In this case, it's error. It's basically saying, on average, summing over all my training data, dividing by the number of samples in the training data, how different is the true answer from what I'm currently predicting with my model under parameters theta? Right? Now, sometimes you might say, well, shouldn't there be some sort of offset, like a constant offset? Like maybe what we want to be able to do is have two parameters. Like you might want to do something like h of theta x of I plus some special value, maybe theta naught, theta 0, which is it just raises or lowers all predictions. But we're not actually worrying about that because we can just add a feature that's always equal to 1. Let's just pick one of the x's and set it to always equal to 1, so that this additional offset, or what's sometimes called the bias term, and this is something that's used in neural networks all the time, by the way, this offset or bias is absorbed into the model that we're learning just by changing the features. And this is actually a really nice trick because like you can just, it's kind of like, you want to do face recognition, right? So you have this megapixel image, but in addition to a megapixel, you have a megapixel in one image where that last pixel is just the value 1. And you just feed it into the model. So you have one extra pixel, which is always a constant, just to allow a little bit of offset, a little bit of bias. And that actually is kind of nice because oftentimes you have toolkits that can be, you don't have to do any different codes. You just sort of give it one more dimension. It's a constant. But we're going to assume that that's done, that this bias has been absorbed into the model by allowing one extra feature to be a constant. Okay, so how do we learn? This is machine learning class after all. This is a model. We want to learn it. We're still in the context of, I don't know what that p is doing there. That p shouldn't be there. So we take the gradient of our objective, j with respect to theta. And now we're actually doing a little bit of calculus. We use the chain rule. It's 2 over n times the sum, and we have this error term, and then we use the chain rule, and we take the gradient of this with respect to theta and set it equal to 0. So, okay, so now the gradient, remember the model itself is just x transpose times theta, which is by the same as theta transpose times x. And we take the gradient with respect to theta, it turns out that gradient is just x. So the gradient of h theta of x of I with respect to theta is just x of I. So what that means is that this whole part here that whole part can be replaced by just x of I. Now that begins to be a solvable thing. Like we can solve that, and we can solve that for theta relatively quickly. And we're going to do that in a minute. There's a linear model. I do want to say, before we actually go ahead and solve this here in equation 1.17, let's talk a little bit about features, right? Because like this is a very simple model. It's a linear model, right? It's basically saying, in order to make our predictions, we take x and we do a dot product with theta. I mean, this is basically a multi-dimensional generalization of a linear function with no slope, right? Sorry, with no intercept. It's just slope. Although we added the 1, so maybe it's like a slope. This is no different in the one-dimensional case than y is equal to mx plus b, right? And it's mx plus b x0, where x0 is always identically 1, right? So b is just a constant. So that means it's a line. It's like, or if it's in high-dimensional space, it's a generalization of a line, which means it's a plane, or it's a hyperplane. So in m-dimensional space, it's an m-1 plane in m-dimensional space. Is that a very complicated model? Is that a very rich model? No, it's pretty poor, right? It doesn't have a lot of capabilities. But what we can do, and this is a fairly, what I'm about to say is a fairly non-neural netty way of fixing the problem, is to say, well, it's linear in x, but the question is, what is x? Maybe x itself is a transformation of what the real input is. So maybe x is not the pixels. Maybe x is some transformation that you've done, you as the data scientist, you've done some transformation to those pixels to turn it into x. And maybe the pixels are called z. And so z is a vector of pixels of an image. You transform z into x, and then you're linear in x. So therefore, but if the transformation from z to x is not linear, then you're no longer linear in z. You're linear in x, but not linear in z. So you can have potentially a lot of flexibility. You can kind of have your cake and eat it too. You can have a lot of flexibility in being nonlinear in the original representation of the data, in this case, say pixels, even though you're linear in the thing that you're learning, to make the learning process easy. So that's what these next bullet points are basically saying. So let's say x is a feature vector that you've acquired through the process of feature engineering, which is one of the critical steps in all machine learning problems. And these are features that have been engineered from some more raw information sources, say z. And say z is a vector in m prime dimensional space. And this is true whether you're doing images or if you're doing audio. Maybe z are the PCM samples of an audio file. Or maybe if you're doing geothermal experimentation, then maybe these are like low-level, uncalibrated, piezoelectric vibration sensors of some sort. Right? There's just a ton of different possible sensors that you can imagine, all of which, when you first look at them, they're really raw and really noisy and really awful, and you want to do something to them to turn them into a nice feature vector x. So that's what I just said. Z might be raw sensor values, pixel values, audio samples, and so on and so forth. Anything close to the sensor. Close or at the sensor, I should say. And X is some feature extraction process. It's not a random process, it's a deterministic process, meaning every time you give it the same Z, you're going to get exactly the same X. Now here's a very simple one. Very simple, it's just a polynomial expansion. So let's say that m prime is equal to 2, and you have a 2-pixel camera. It's not a lot of pixels, but so this is the first pixel and this is the second pixel. And you transform this 2-dimensional space into an m-dimensional space. And how do you do that? Well, let's say that x1 is just identically equal to z1, and x2 is identically equal to z2. But then x3 is equal to z1 squared, and x4 is equal to z2 squared, and x5 is equal to this should be multiplication here. x5 is equal to z1 times z2, so it's the product of the two features. Then x6 is equal to z1 squared times z2, and x7 is z1 times z2 squared, and so on and so forth. x8 is z1 cubed. So you can see that in terms of z, you're doing a nonlinear transformation. It's a polynomial transformation of the z's to the x's to get a higher dimensional x space, starting from a very low dimensional z space. And so the kind of classifier, even though you're linear in x, you're no longer linear in z. So this is, and you could sort of represent this as a feature extraction process, like phi is a feature extraction process that goes from the sensors and maps it to the features. This is used ubiquitously, even with neural networks. I said this is a very non-neural netty way of doing things. So even with neural nets, you do this still most of the time. Usually you do some form of feature extraction before you feed the data to a neural network. Although a big push in the neural network community is allowing the neural network itself to learn phi. So phi, right? Like phi is usually like hand designed. In fact, there are thousands and thousands of papers in the machine learning community on how do you choose Z. Sorry, how do you choose phi function? How do you choose the feature extractor? And there's different papers for different types of data. For audio data, there's one kind. For video data, there's another kind. For sensor data, there's still another type. For medical data, for all these different data, for biological data, for genomic data, for genomic data, you have different types of feature extraction mechanisms. And the only way of knowing what works is to either try it or to read a paper of somebody else who's tried it for you. The neural network approach, the more recent approach is to say, well, why should the human be burdened with selecting phi? Let's let the neural network itself learn it. And neural networks are flexible and powerful enough. And sometimes that works, and sometimes that works better. But at the same time, you're now putting the burden on the neural network, and sometimes it just fails miserably. It says, I have no idea what to do with these features. I need some assist. And that's where the data science comes in. You have to think about, become friends with your data, get to know your data, understand your data, and hypothesize about what would be the right representations and transformations of your data to make the rest of the machine learning model's job easy. That's feature extraction. So someone asked during the break about representation learning. So the idea of representational learning is the idea of essentially automatically, let me just write that term down. Right, so the idea of representation learning is to automatically produce a feature extraction mechanism. So you're automatically learning. It's like this is the raw features, and you're automatically learning a representation. X is the representation of Z, and this transformation phi is learnt automatically. So you're learning the representation of Z, which is X. And you see these days, I mean, representation learning is from the perspective of machine learning, it's a relatively new term. New meaning the past 10 years. It's funny because sometimes I hear really young machine learning researchers say things like, "Oh, that technique is 6 months old. It's ancient." And I think, well, wow, there's still methods that are 25 years old that are still used today, like PCA. People were doing PCA back in the 60s, and people still use it on a daily basis. So you should never think, and when you think about mathematics, I mean, mathematics is hundreds, maybe thousands of years old, and people are still doing it today. So just because something's older than 6 months, by the way, the person who said that was probably around 19 years old. So 6 months is a long time for a 19-year-old. Right? So just because something is older than 6 months doesn't make it bad. There are many extremely useful techniques that go back to the 60s or the 70s or the 80s or the 20s or the 1800s even. But representation learning is a relatively new term for learning a representation of your input. Okay, so let's go back to our linear model. So we're linear in the representation X, but means that we're nonlinear. We're nonlinear in Z, because H theta of X is theta transpose times phi of Z. And if theta transpose is a nonlinear function, it's a fixed nonlinear transformation on Z, so therefore we are nonlinear in our original input. And that basically means that the power of linear models can be greatly extended beyond what you think about as just a simple linear map or a hyperplane, right? But with that power comes responsibility, right? Just like all power. And if you grant a model such expressiveness and power, the problem happens, which is that the linear model can eventually, if you have enough features perfectly fit the data, and you can overfit. Overfitting is a concept that we're going to define very formally, either later today. I think we'll make it later today if we end. But overfitting basically, I mean, just before we formally define it, is basically the phenomenon that happens in machine learning systems where your model does so well on your training data that it does terrible on anything but your training data. So the idea being that you might perfectly fit your training data. Now, it doesn't perfectly fitting your training data doesn't necessarily mean that you won't do well on other data. But overfitting basically means that you do perfectly well on your training data and you do terrible on anything other than your training data. But there could be some other model that does less well on your training data but does really well on all the other data. Right? So that first model that did perfectly well on your training data or did very well on your training data is said to have overfit. It fit too tightly your training data. And so therefore you need to deal with it. And what can happen is if you do too much feature engineering, if you have too high a dimensional space because of your features, there's the potential for overfitting. We'll talk about this in a minute. Any questions on overfitting? I mean, this is a concept we're going to visit several times in this class, also associated with bias variance, which is a really fundamental, critical concept to understand in all machine learning data science, which we will talk about in a lecture or two. Okay, so let's go back. Actually, no, I just asked if there are any questions. Are there any questions? Are we at a section transition? No, we're not at a section transition. But this might be still a good time to pause for a compulsory question. Yep.
Is there a good way to allow for a feature that isn't in your data?
Well, the features. I mean, you mean a feature that's not in your data? Because we get to decide the features, right? So, like, for example, let's say we have Z1 and Z2. So you might decide I want to have Z1 squared. So is as one of my x's, right? So is Z1 squared in your data? I mean, all of those other features that you've decided, which are transformations of your z's, are in some sense not in your data because they weren't in the original representation. So, like, if you have a sound sensor, right? And one of your features might be squaring the samples. Like the samples could be positive and negative, and you say, okay, the first thing I want to do is square them, and use the squared samples. I mean, that's kind of not in your data.
I was kind of thinking, like, with the house example where you say we're just going to look at the size and the number of bedrooms, but you kind of know in the back of your head there's other features.
Well, so that's different, right? So, like, in that case, we actually have new raw sensors. So think about it like that. That's a great example. So, like you just said. So, let's say we have houses and number of bedrooms, and then maybe does it have a basement, right? But here it's saying, well, maybe to learn the classifier, it would be good to have not houses. It's like squared area, right? So the squared area, number of bedrooms, and does it have a basement? But and what you're trying to do is predict house price. But maybe having the area squared, right? So rather than 400 square feet, it's 400 squared. Squared, feet squared, whatever it is, right? Square feet. It's feet square, I guess it is. And then maybe number of bedrooms. Instead of 3 bedrooms, it would be the number 9 because you're squaring the number of bedrooms, or you're multiplying the square feet by the number of bedrooms. So it's like feet bedrooms or something. We have a new feature called feet bedrooms, which is derived from the features you've got. So the feature engineering process is basically saying, okay, I've got these inputs, these z's. How do they transform them into an x, which is the one I'm going to use for my machine learning system? But the z's, like which z's am I going to choose? Like the square feet, or the number of bedrooms, or does it have a basement? Those are the z's in that case. Right. So we might learn a model just on those z's and do no transformation at all, or we might do some transformations on those features before we actually learn a model. And that's this process here. So in some sense, it's a little bit sort of a blend between, on the one hand, taking the square of a z is not really in your original data, but it's derived from your data. So it is kind of in your data, but it's different than, say, getting yet a completely different information source. But there's still a lot you can do with this, right? There's still a lot you can do with feature transformations. One of the things actually from information theory, I mean, it's sort of a useful result. Like, you can't get any more information about your source by doing further processing on it. But what you can do is make the representation of certain functions easier. Like, suppose it really is a nonlinear function that you're after, but you're forced to use a linear model. So then by doing nonlinear transformations from your input, you can still be nonlinear in your in your z's, even though you're linear in x's, and then get that nonlinear function that you need to fit the data better.
So is that when you went over, like you could just multiply by some nonlinear function and then get a perfect fit or perfectly linear?
Well, let me give you another example. So let's say, how do we add a page here? Sorry. Okay, so let's say your data, let's say your model is y is equal to x squared. Okay, and you take samples. And so this is truth. So if you're to take samples, and let's say it's x squared plus some noise. So epsilon is like noise, measurement noise. And so your samples are going to look something like this. Right? That's going to be your sample. It's not going to be, for every given x, you're going to square it and add some random Gaussian noise, and that's going to be y. And maybe that's one, like maybe your data comes from, your data is basically a bunch of x, y pairs. So it's a bunch of samples. So what you have is the x value and the y value. Right? So now if you learn a model y is equal to theta x, the only kind of model you're going to learn are linear models, right? No matter what you do, you're not going to get that nice parabola, because even though you have all of the information to learn a perfect model, your input. Actually, let me change the notation to be consistent with what I was saying earlier. So rather than x, let's use z. So this is the z-axis, and this is y. So we're trying to learn to map from z to y. But if we were to try to learn a linear model in z, it would always do terrible. But then you might decide, you've taken this class, and say, I think we should maybe try squaring it. Maybe you've done some plotting in Python or something, and you say, well, maybe squaring it. So now you come up with a new data set, and you're going to say that x of I is equal to z of I squared. So now, and it's a very simple transformation. You're just squaring the input. And so now what model you're going to learn is y is equal to theta x, which is really equal to theta times z squared. That's going to do really well. You're going to suddenly learn your learning error rate is going to go down dramatically just by doing a simple deterministic transformation on your z. And so you haven't actually added a new z. You haven't added another source. Like z is still one-dimensional, but you've transformed z in a way so that your linear model is nonlinear in the original features. Does that make sense? Okay. So now the question is, how do we optimize it? So a while ago we talked about, there's this slide over here. Remember this slide? So we had this equation, and we didn't have the p, and we said it's this whole thing, and this turns into an x, right? An x of I. So let's write that equation down. In fact, I think I can actually copy this. Let me see if this works. Okay, so then there was the equation we saw before down here, and here it is with x written out. Okay? So now we can solve it. We can solve it and set it equal to 0. But in order to do that, let's represent it in matrix form, because it turns out that matrix form, even though it might seem complicated, actually makes it a lot easier to solve. So each one of these vectors, these are m-dimensional vectors, we're going to take their transpose and represent it as a row. So it's going to be an n. So every sample is going to be a row, and the number of columns is going to be m. So it's m by n. Right? And since we're predicting a scalar, y is just going to be n scalars, right? y1, y2 up to yn. So now we have a vector, x, which for a variety of reasons is called the design matrix. So x is called the design matrix, and we have a length n column vector, y, or y vector. And what we're going to do is then we're going to represent this problem using matrix vector notation. And in order to do that, that makes you dizzy, doesn't it, to do that? This is this new app I'm using. So to represent it, we can actually express the objective in equation 1.18 is basically just this. It's 1/2 times x times theta minus y vector transpose times x theta minus y vector. And so that quantity here, this quantity here, is exactly the same as this thing here. And so then we can say, okay, well, we want that to be equal to 0. Sorry, I made a mistake. That is the objective j. That's not equal. What I just said was incorrect. This is the derivative of this. So this is the gradient of j with respect to theta. This is the original objective, which is the sum of squared objective, which was shown here, I believe. Yeah, this is the derivative back here again as well. But before we took the derivative, that's exactly equal to what j is here. Okay, everybody with me? So what we can do then is use matrix vector algebra to say this derivative here can be expressed in matrix vector form. And we do it in matrix vector form, then we can actually find the optimal solution using relatively simple matrix inversion and matrix algebra. It's like, how do we solve this thing? Well, we express the derivative, and the derivative basically is x transpose times the quantity x theta minus y, and that should be equal to 0, where 0 is the 0 vector. Okay, so that equation, so equation 1.21 here is the same as equation 1.18 here. I'll just zoom in so you can see them a little closer. All right, so 1.21 here is the same as this equation, except that this is the matrix vector form. Now, why do we like the matrix vector form? Because it gives us an easy way to get to the solution, and it also leads to some useful observations. Like, for example, notice that y is the thing that we're trying to predict, and this is the model that we're trying to predict from. And so when you do something like, when you do x theta, I always like to think of matrix vector. I usually like to draw these pictures. So I think of x as this thing here. So this is x, and theta is a vector. And this is the output, right? This is what we're trying to do. And it's kind of hard to do this on the screen, so this is going to be bad for the YouTube people, because I need 2 hands to draw this. This matrix vector multiply is kind of like taking this column vector and this row vector and doing a dot product to go into this element here. And this column vector and this row vector do a dot product to get into this element here. And you're just repeatedly doing these dot products, sliding down. It's always the same vector over here. This is going to be theta, but it's just a different row of this x until you get to the very bottom of this vector down here. And that's matrix vector multiply, right? And so that's what x times theta actually represents. And I guess if you're watching this on YouTube, I should attempt to do this again on YouTube, because If you're watching this on YouTube, you're going to be very frustrated. So what I just did is I said this vector times this row gives us this element, and this vector times this row, this is the dot product. These are two vectors, gives us this element, and this vector times this row. Sorry, this vector times this row gives us this element, and so on and so forth until we get to the bottom. That vector times this row, dot product gives us this element. So in some sense, you can sort of think of this as saying, let's say that this x is equal to x1, which is this column vector, x2, which is this column vector, dot, 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 and m, which is this column vector. So that matrix X can be represented as a bunch of column vectors, right? And so we're saying it's the column space of matrix X, because in some sense what we're saying is that this answer is equal to the sum for j is equal to 1 to m of x of j times theta of j, where theta j is a scalar. Right? So we're just basically summing up these columns to get this column. So it's some value, it's a weighted version of this scalar, a weighted version of this vector times plus a weighted version of this vector plus a weighted version of this vector, and so on and so forth. Each one of these vectors all added up with their corresponding weights, which gives us this final vector. And that final vector here should be as close to y as possible in order for the error to be 0. Okay, that's a lot of discussion about this equation. But what the slide says is that it's called the normal equations. And we haven't said, well, why is it called the normal equations? Well, the way it's called the normal equations is because of this picture. So that column space, let's just copy this out here. So there's the column space. That corresponds precisely to this yellow box. You can say that these are all y's. This yellow box. This is in low dimensional space. We're trying to visualize a high dimensional thing by looking at it in low dimensions. So this plane here corresponds to all y such that you're taking a linear combination of the columns in this form. So this x times theta is just this, right? This is equal to x times theta. So those are the possible y's we can get. What we're trying to do is find a theta hat that minimizes this, that's as close to y as possible. And as we're moving around in this plot, we eventually get to this one. This is the true y, and it's not necessarily the case that y actually lives in the column space. Like there might not be any value of theta that sort of perfectly lives in this column space. What we want is this whole thing to be equal to 0, right? But what we ended up getting is something that's orthogonal, right? So that this error is orthogonal to the column space, right? Because anytime we have this vector, so it's y hat minus x theta tilde, which is the same as this thing. I mean, that being 0, it's basically this thing, it's the error. That being orthogonal to the column space means that this equation is going to be 0. Right? Because whenever you have orthogonal things and you take dot products, you get 0. And so it's called the normal equations because this error term is normal, or it's orthogonal to this column space of this column space of x. And where the column space is defined by all possible linear combinations of the columns of the vector x, of the design matrix. So this is a really famous equation. You guys should absolutely, I should, like if you go to Facebook or Google or something and you want to interview and get a job at a place like that, they'll sit you in a room and say, okay, derive the normal equations. And if you can't do it and if you fumble, they'll say, sorry, we won't hire you for a machine learning job. So you have to be able to derive this from first principles, and you really need to understand this. It's a classic kind of Facebook, Google, Apple machine learning question you might get. And they'll ask you to interpret it too, and you'll need to draw this kind of picture. So now how do we actually solve it? This actually characterizes the solution. But the way that we solve it is, it turns out that this matrix, X transpose X, is typically invertible. Typically whenever it's the case that n is much bigger than m, and usually it is the case that n is bigger than m. So we can write this as X transpose times X theta minus, sorry, did someone have a question? Oh. Let's just write this. I'll zoom in again. Maybe you can't see the writing. So it's X transpose right. So if we can invert this thing, we multiply both sides by just X transpose X inverse, then we'll get the solution. We'll get the solution for theta. And so theta, the best theta is equal to X transpose X inverse times X transpose from Y. And this is the solution to the normal equations. It's also sometimes known as the Moore-Penrose pseudo-inverse of the matrix X, but the main point is that it is the solution to the normal equations. And it's something that we can solve relatively simply, analytically, using matrix inversion. I mean, is matrix inversion an analytic expression? Usually you need to use numeric procedures of some sort to do a matrix inversion, but certainly if you're coding this in Python, I mean, you can get matrix inversion instantly using NumPy. So the solution is readily at hand. And this is the optimal solution. It's the one that minimizes the error. So that's it. That's linear regression. That is your first associative memory in a machine learning sense. It associates from X to Y. We talked about feature extraction, which is how do you get a good X. Even though it's a linear model, and it's a relatively simpler model, if you do a good job with feature extraction, you can still do something good. Now, linear models are still used a lot. I mean, in fact, when you think about something that you need it to be really fast, and there's some evidence that Google's search algorithm is using a linear model. And every time you do a Google search, it's just a linear model. And why do they use something as simple as a linear model? Because it needs to be fast. It needs to be, and linear models are very, very fast. The feature extraction can be done in parallel. The feature extraction can be done before you actually do the model. And then you can have a really optimized matrix vector and matrix multiply are some of the things that can be made as, so there's some of these are the types of numeric computations that can be made ridiculously fast. They're fast on CPUs, they're fast on GPUs, even faster, much faster on GPUs. And so therefore linear models are still widely used. But if you insist upon using a linear model, in order for it to be accurate, you need to do a good job with the feature extraction. Right? So, right. Okay, this is a time for questions now. So I'm just going to stand here and wait until somebody asks a question. A question?
The process of reducing error, aren't you also sort of overfitting the data?
It's possible, yeah. I mean, if you have too many features, like if you start with Z, and Z, like the example we gave was Z was 2-dimensional, and we made X m-dimensional. And if m is much, much bigger than 2, like what if m was 1,000,000? Chances are we would perfectly fit the data and we would overfit. But you're not necessarily overfitting the data, because maybe X is not too many more features, or maybe X is equal to Z even. In which case, one of the things about a linear model is that we're going to learn about overfitting and bias invariance. Linear models, ignoring for the moment what I said about the feature extraction process, tend to have what's called high bias but low variance. And such models are not likely to overfit. High bias, low variance model. Now, what is bias and variance? We're going to spend hours on that. That's like I said, that's one of the critical concepts in machine learning that you need to understand. So to answer your question, yes, it's possible we might overfit, but it's not guaranteed, and we can be careful not to overfit if we're good, if we're smart, and we understand bias variance, which we will. But I don't want to digress too much on bias variance because we will spend a lot of time on that. Okay, good questions. Let's move on. Okay. So linear least squares is what's known as a batch algorithm, right? It uses all of the data at the same time, and it requires random access to the data. You know, like when we're doing this matrix inversion process, we need to load all of the data in, you know, let's say we're doing in-core matrix inversion. We need to load all of the data in core, in memory. And we need to do a big giant matrix inversion. And if it's the case that, say, you know, so like, let's say that n and m are both big. I mean, first of all, doing this step might be complicated. And even though it's the case that, you know, this matrix is only m by m, right? So this X transpose X is an m by m matrix, and maybe m is not as big as n, but m might be pretty big. M might be, you know, 1,000 or 2,000 or something. So that means that you would need to have a 1,000 by 1,000 matrix and do an inversion on that. And matrix inversion can sometimes be costly. You know, maybe sometimes matrix inversion can be cubed in the dimensions of the matrix that you're inverting. So it would be like m cubed. That could be expensive if m is 1,000. Not to mention the memory and the random access. So online algorithms are different than batch algorithms. Online algorithms kind of learn one step at a time, one sample at a time. And most machine learning algorithms these days are not batch. In fact, almost all neural network algorithms are not batch. These are all online algorithms in some sense or another. The famous workhorse of deep neural networks, stochastic gradient descent. Stochastic gradient descent, which we're going to talk about in a minute, that's an online algorithm. So what do we mean by online? And how do we learn one step at a time rather than all at the same time? What does that mean? What does online mean? Oh, sorry, there's another bullet point. The other thing is, like in the batch case, in the linear least squares case, it was possible to represent the solution analytically using matrix inversion, matrix vector algebra. But there are many objective functions whose minimization has no online solution. Like if we take the gradient of j with respect to theta, and we set this equal to 0, and try to solve for theta, it won't work. It's not solvable analytically because there's too many nonlinearities surrounding the theta values. So we have to do something else. We can't just solve it all in batch. The other thing is that, you know, online or what are sometimes also called streaming algorithms, they don't have to fit all of the data in memory at the same time. You can be learning as things come in, and there are many machine learning settings where you're perpetually learning. Like you have a model and you have new data that comes in. Every day you have new data that comes in, and you only use the data once, and you throw away the data because you have so much data that's constantly flowing and streaming into your machine learning system that you can't afford to use your data more than one time. So it comes in, you learn from it, you throw it away, and it's like this never stopping flow of data that comes in. And so on a batch algorithm would just never work, because a batch algorithm would require you to say, okay, stop, use all of the data I've got, and learn from that batch. Because there's never a point where you stop. You never reach the end. Whereas online algorithms can be learning as data is coming in. So the idea is to not try to set this equal to 0, but what you try to do is you nudge theta to be in the direction where you know the gradient, where the objective function is smaller. Like you're sort of slowly moving theta along to minimize the objective. Ideally, moving it to the point where it gets smaller, and so you minimize. You're trying to shrink the gradient, I mean, in some sense or another. So how do we do this? So let's say we start from some initial estimate of the parameters theta, and we have what what we could do here is we can, for all individual values, we can say, okay, this is the old, for all individual values of theta, we can say take the old value of theta and subtract away alpha, where alpha is what's called the learning rate, times the gradient of the objective with respect to theta j. And then we come up with a new version. So theta j gets updated with the old version minus alpha times the gradient of the objective with respect to theta j. And this gradient is just, the same gradient that we saw before. And I think this is again another typo here. So that shouldn't be there. But the gradient, we plug in the definition of the objective, which is this thing here. It's the squared error. We take the gradient, and this becomes the final answer after we solve this algebra. So it's basically the error times the jth value of the vector x. Now this is actually kind of interesting, because basically what it's saying is that this is the update rule for all j. That we're kind of adding the jth element of the vector to the jth element of the parameter, weighted by alpha times the error. And if the error is positive, then we're adding a positive amount of xj. And if the error is negative, we're adding a negative amount of xj. So either way, we're kind of sort of adding more or less xj. And also it depends on the magnitude of xj, and it depends on the magnitude of the error, and of course it depends on the learning rate, how quickly we want to learn. And in fact, we can do this for all of the elements of theta at the same time, and we get this update rule. We get the theta vector the new theta vector is equal to the old theta vector times alpha, plus alpha times the error times x. So we move theta in the direction of the sample weighted by this quantity here. If we're doing well, and obviously if we're doing well on that sample, like if the error is 0, if we're predicting perfectly, we don't adjust theta at all for that sample. Because it basically says, oh, you're doing perfectly, you don't want to adjust it at all. You don't need to, because you're already doing well. You're only adjusting things on those samples that you're doing poorly on, where poorly is basically measured by this error, and the sign of poorly depends on whether it's positive or negative. Right? So this is called least mean squares. The least mean squares rule is also called the Woodrow-Huff rule, and it was actually a very early neural network learning technique for very simple, because I mean, after all, a one-layer neural network is basically like a linear model. So kind of like what we're doing, there was a question as, are we going to do neural networks in the class? We are kind of doing neural networks now. We're doing single layer. We're doing very, very shallow neural networks right now. And this learning rule is a standard learning rule for such models. And in fact, it's actually the root of all learning models. It's basically gradient descent. Now, batch gradient descent would be to do the following, where what we do is we repeat the following thing 3 times. This is one thing I want to mention, is that this is called, the next thing we're talking about is batch gradient descent, because we're going to compute the gradients of all the samples simultaneously before we update our parameters. So the new theta is equal to the old theta plus alpha times the cumulative gradients of all of these things, right? So this, why do we say this is the gradient? Well, because that's basically the same rule that we did here. We derive that by computing the gradient of the objective. So this is batch gradient descent. But this would seem to be not addressing all of the problems that I just mentioned. This is not an online algorithm, right? Because it basically, before you update any parameters, you need to get all of the data. What if it's a stream? What if n is unknown? Or what if n is unboundedly large? Right? You could, this is partially streaming, because this is something you don't need to store everything in memory. Like, as the x's come in, you could compute this, and then this could be an accumulator, and you accumulate this thing until you're done. So you don't need a lot of memory, but you do need to have a fixed size data set, which is n. So it doesn't work for streams, and it's not really online. And so what batch training does, I mean, here's an example. This is an example of the parameters. So this is just simply fitting a line to these samples. So we have square feet and price, and so we have two values. We have the intercept and we have the slope, right? So this is essentially, it's fitting y is equal to mx plus b. And what this plot here is showing is m and b, and showing how it converges to the optimal solution. Right, so every single step, we start here, we jump over here. I can zoom in a little bit on this one. We start here, and after one batch gradient update, we move over there, and we move there, and we get closer and closer and closer and closer until eventually we get to as close as we want to the true optimal solution. At least true optimal for this data set, right? And here's some examples of other starting points. Like this is again batch gradient descent. If we start here, we move towards the solution this way. If we start here, we move towards the solution this way, and so on and so forth. But no matter where you start, you're going to move towards this solution. And that solution is going to be the one that minimizes the objective function, minimizes j.
That's theta.
Yeah, this is theta. You can think of this as theta 1 and theta 2. I don't know why it's written as xy, but it's basically the same. It's the same thing. Maybe let's get rid of the xy. I mean, in this example here, we're fitting m and b, and so theta, in this particular case, theta is equal to theta 1 comma theta 2, which is equal to m and b, where m is the slope and b is the intercept of the line. We're just renaming the parameters theta. Theta is kind of a generic name for parameters. There's two variables that are typically used for parameters in machine learning models, either theta or w. Oftentimes, and we'll probably use that too. Sometimes w is a vector parameter, sometimes it's theta. Those are the most commonly used variables to represent parameters. In the case of a line, when you learn, when you're in junior high school, you learn about mx plus b. Okay, so that's batch gradient descent, and pretty much where you start, you get to the solution. What stochastic gradient descent is all about is to say, well, what if I don't know how long the stream is? Or what if I want to start updating my parameters as soon as the data gets in? As soon as I have a sample, I want to make a parameter update. I don't want to accumulate all of these updates and then update theta all in one go. I want to do incremental updates. And in fact, sometimes, in the mathematics community, this is called incremental gradient methods. And the reason why it's called incremental gradient is because we're incrementally updating theta. So the idea is here there's a loop over the data, and for every sample, we do just the gradient of the objective with respect to that one sample, and we update theta there. And so this is a little bit different, right? Because what it means is that for the next sample, we're taking the gradient of the parameters that have been updated from the previous sample. And on the third sample, we're computing the gradient that has been updated from the first two samples, and so on and so forth. So by the time we get to the very last sample, the parameters are going to be in a very different state than they were at the beginning of this block. And this is called, by the way, this is called an epoch. And so this basically says repeat for t epochs. So we're doing capital T epochs through the data. Each epoch we do one complete pass through the data, and we're doing incremental gradient updates. Or we're doing stochastic gradient updates. By the way, officially, I'm kind of being a little bit imprecise here, but what makes it stochastic? So right now, there doesn't seem to be anything stochastic in this algorithm. The stochastic part of this comes by choosing a random order. So if we randomize the order, in fact, ideally potentially randomizing it at each epoch we choose a different random order, that's what stochastic gradient descent is. And that is the method. The stochastic gradient descent is the method, or some version of stochastic gradient descent, is the method that all machine learning successes that you've heard about, all of the major successes, all the deep fakes that you've read about, and the death metal music and everything, Everything that machine learning has achieved has been achieved through stochastic gradient descent. It's amazingly powerful and simple technique. Now, it's not a linear model. It's a neural network or some other nonlinear model or gradient boosted decision tree of some sort. But it is still this general approach where you take the incremental gradient of a sample and update the parameters, and then repeat for the next sample. So what does it look like? I mean, it looks somewhat similar. It's like this is the thing. Let's just look here. So notice that, like when we did incremental gradient, when we did batch gradient, each one of the steps is kind of in a good direction, right? Moving towards the solution. But because of some stochasticity and some randomness, sometimes we're making mistakes. Like look at this guy here. The best direction for him would be to move there. But because we're taking a gradient step only in the direction based on that one sample, we're taking a misstep, or at least we're not going in the most optimal direction. It would be faster to go here. But at the same time, there's a lot of reasons why stochastic gradient descent is preferable, because in this particular case, the solution is obvious. Oftentimes the solution is not obvious. And the other thing is it's computationally, it's easier to compute, it's faster. We can start working on the learning process right away. We don't have to wait for all the data before we start learning. And so therefore it's in some sense more efficient. You get more learning done per flop, per floating point operation with stochastic gradient descent than you do with batch gradient descent. And you kind of think of it like you want to get the most learning work done for every single floating point operation you do. And stochastic gradient descent has kind of proven itself to be the most efficient in terms of work done per flop, per floating point operation. And on average, even though you're making these local mistakes, on average you're going in the right solution. Now, of course, there's some problem here. Is like when you get near the solution, you bounce around a lot. There's variance. There's a lot of variance of the solution, and we have to be smart about that. I mean, in this particular case, we used a fixed alpha, a fixed learning rate. In order to keep things from bouncing around, especially when we get very close to the solution, we should be shrinking alpha, so that we don't want to move quite as much as we get closer and closer to the solution. And so a lot of methods, some of which we will talk about in this class, are forms of what are called adaptive learning rate schemes. Like you might have heard of them, things like AdaGrad and Atom and a bunch of other methods. There's a bunch of other methods that do things like stochastic gradient descent, like smoothing methods, variance reduction methods like Saga and SVRG. These are all methods that in one way or another essentially reduce the variance, and one of the ways of doing that is to shrink alpha as you do more and more learning. Like one simple form would be to set alpha and have it be I dependent, which is like have it be t dependent and have it be 1 over t. So for each epoch, you decrease the learning rate with t, and that's kind of an agnostic learning rate shrinkage thing, as opposed to an adaptive one. It's agnostic because at every epoch you're using a smaller and smaller learning rate, so eventually at the very end you're not jumping around so much, like what you see here. I mean, if you zoom in on this, you can see really that there is a lot of jumping inside at the bottom. Like you won't necessarily settle on the right solution unless you shrink. Okay, so I should also mention that between batch and online, there's the method that people actually really use is what's called mini batch gradient descent. And there what you're doing is you're not taking the gradient using just one sample at a time, which would be full online, nor are you taking the gradient with respect to all of the data, but you're taking like a bundle or a bunch or what is called a mini batch of data, which could be 4 samples or 16 samples or 32 samples or some number of samples. And you take the gradient with respect to that, and like in this particular case, we're saying the data is the index set 1 through n, and we're partitioning the data set into these bunches or these mini batches, v1, v2 up to vk. and they're about the same size, usually. I mean, we want them to be roughly the same size. So it's a evenly broken apart partition of the training data, and then each gradient step update we rather than sum over each epoch is rather than summing over all samples, we sum over all blocks in the partition. So here we've got k blocks in this partition, and we're summing for, we're iterating over for L is equal to 1 to k, and then this is the gradient with respect to the lth block down here, because we're summing over only those samples in the lth blocks. Now, why might we want to do this? Well, because first of all, it gives us a nice trade-off between full online and batch. But there's one critical thing, one critical reason that you might want to do this. It's that it's faster. It's faster computationally, because what we can do, like this can be, generally speaking, the fastest the fastest compute you can do in terms of the closest to the fastest the machine can be is when you're doing matrix multiply. When you have a matrix times another matrix, and the solution is, and you're multiplying that into another matrix. So this is matrix times matrix is equal to matrix. If you can organize your compute into matrix multiply, you can take advantage of extremely good libraries, not to mention that matrix multiply itself is one of the most amenable kernels of computation for high-performance computing. If you're doing full online and only online training, you can still take advantage of it to some extent, but you're doing matrix vector multiply. So you're doing this matrix times this vector is equal to this vector. It can be made to be fast, but not as fast as matrix multiply. And so when you're doing mini batches, you can actually organize the computation into matrix multiply, and therefore you get more. You're just using less energy. You're getting much closer to the theoretical peak performance of your machine, whatever the machine is. And this is true whether it's a CPU or a GPU. GPU, of course, matrix multiply just flies. It's just ridiculously fast on GPUs. And even CPUs can be made. CPUs with floating point units can be made to be extremely fast when you're doing matrix multiply, much faster than if you're just doing vector dot products or matrix vector. Right, so that's the idea of mini batch. Okay, there's one other thing I want to say about linear least squares. This isn't so much. Actually, I should probably pause at this point before I go on, because the next one is just going back to normal equations and Gaussians. But let me pause and ask for a compulsory questions. Yeah, question.
So I was wondering, when we do mini batches for stochastic gradient descent, do we pick the same samples into a batch, into a given batch, or do we randomly select samples and then create our batches and create all of, is that how that works?
Yeah, I mean, in practice, I mean, in theory, what you generally want is the mini batches to be unbiased samples of the full thing. So you could, for example, take random subsets, right? And ideally, you take like a new random subset, like you take a uniformly at random subset, and then that would be your mini batch, and you do that with replacement. But there's other things that you can do. One of the things that you can't really afford to do is redo your mini batches each time. Like you can't, data sets are so big, like let's say you've got this massive data set, and let's say it's 1 trillion samples. I mean, real world data sets can be very, very large. Let's say it's 1 billion samples. So you've got 1 billion samples, and you can't afford in between epochs to reformulate your mini batches, because just reformulating the mini batches in the first place itself takes too long. So what people typically will do in such cases is just take the batches as they come. But that can be very suboptimal, because you can have correlations, meaning that they're not sort of uniformly at random. They're very far away from uniformly at random, unbiased samples. What they are, you can actually have these regions in your data which is very correlated. And as you're training on these mini batches, as you're going through the data, the model is going off thinking all it needs to do is learn this stuff that's in the first part of your data. So by the time you get to the second part of your data, your model has sort of drifted off into Never Never Land. And if it's a nonlinear model, then it might mean another local minimum, and so on and so forth. which it might get you to a point that it's impossible to recover from. Or if your model, even if it's a linear model, like a linear least squares model, your gradients, even if it is the case that eventually it corrects by going through all of the data, which it would in this case, it would be slower, right? Because you spent the first part of your training sort of doing wrong gradients. And if you truly did stochastic gradients, yeah, you'd make some errors, but on average, even a local averages, you'd be pointing in the right direction and moving towards distribution. So one of the research questions that people are interested in is, well, how do you form your mini batches? I mean, let's say, okay, I can afford to form my mini batches once and only once, but then I have to suffer the consequences of whatever they were. And most people resort to random sampling or some sort of random permutation. But they're not even in practice. They're usually not perfect permutations, because taking a permutation over a billion elements is itself a truly uniformly at random permutation, or a billion elements is itself a very complicated problem, very costly problem, I should say. So usually you approximate that in some way.
Is it worthwhile to every once in a while, like, let's say you train the model and then achieve some sort of accuracy? Is it worthwhile to rebatch and then try to train again to see if you can?
It can be, but you know, there's the expense of rebatching, right? So there's the computational expense, and you know, these are, you know, machine learning involves a certain amount of computing systems, right? And to really be a good machine learning researcher, you should understand memory hierarchies and computer architecture and operating systems, and realize, okay, everything is in a memory hierarchy. There's the registers, there's the L1 cache, L2 cache, L3 cache, there's the translation look-aside buffer, there's the pages, then there's the disk, there's on-site disk, and maybe you've got a sort of like an SSD solid-state disk that's big, but then you've got sort of less expensive but much bigger traditional, you know, magnetic disk that's slower, and then maybe, you know, it's a network, so the rest of your data is in your New York office, right? Because for some reason. And so you somehow need, you know, if you were to rebatch all of that stuff and reaching out to the New York office and the Phoenix office and so on and so forth, that would be very expensive, just because you'd have to somehow get all of the data from everywhere. And when you're working on really big data problems, it's just not worth it, you know, because you spend all this time rebatching. Meanwhile, the model's sitting there, well, I'm waiting for my next gradient update data, you know, the model's not able to do anything, so the model has to sit there idle, and the training process has to sit there idle. And one of the reasons why stochastic gradient, it's kind of a trade-off. Like, is it better to do more wrong work or less right work? Sometimes it's better to do more wrong work. Maybe that's even a lesson for life, you know. But in machine learning, it's certainly a case that sometimes it's better to do more work sooner that's not perfectly correct than it is to wait for the perfect mini batch scheme. But on the other hand, it's still a research topic, right? Which is, you know, if you can do your mini batching once or your ordering once at the up front, and you can say, okay, well, you have one opportunity to decide what data goes to New York, what data goes to Phoenix, and what data stays in Seattle.
Do that in parallel would be pretty good.
Yeah, I mean, there's network considerations, there's time. You know, maybe you want to do it on Sunday nights when nobody's using the network or something. But that is sort of a research topic. But it's and it's actually one that, to be honest, greatly interests me. But it's it is still there's. By the way, I should also mention, and this is something that you should all realize, that, you know, machine learning is right now a very rapidly evolving and changing field. Every year there's thousands of new papers to read and thousands of new techniques, some of which are very bad, but some of which are very good. So it's like you really have to be willing to do a lot of learning to stay current in the field, just because it's evolving so rapidly. There's a lot to learn, but there's a lot of old stuff to learn, but there's a lot of new stuff to learn. And sometimes, by the way, I can definitely empathize with feeling overwhelmed by how much there is to learn. But, you know, no matter how little you know, just remember that there's always people who know less than you. So just try to remember where you were and where you are. So all right, so let's just do one last bit on the normal equations. So I wanted to mention that actually, with a very simple Gaussian model, we get the normal equations too. So let's go back to our linear regression problem, where we have yi is equal to theta transpose x of I, but what we're doing is we're adding a little bit of Gaussian noise. So epsilon is a Gaussian random variable, and here's basically a simple scalar one-dimensional Gaussian, and that's the noise that we're adding to it. And so what we can do then is represent the problem as a probability distribution. We can say, okay, well, given theta, what's the probability of y given x? And that turns out, that conditional distribution turns out to be a Gaussian, with because the mean of this Gaussian is 0, and the variance of this Gaussian epsilon is sigma squared. And so that's where we get the variance from. So we can then do a form of maximum likelihood estimation. Since now we've got a probabilistic model, we can now say, okay, well, we on the one hand, earlier we tried to find the thing that minimizes the error, and that gave us our normal equations. But what if we try to do a maximum likelihood solution? So let's represent the likelihood. So the likelihood of the data given the parameter theta is this, right? It's just it's the log of the product of the probabilities. And we take the log and it turns it into a sum. And we take the derivative of the likelihood function with respect to theta, set it equal to 0, and what do we get? We get exactly the same normal equation solution. So this, we're not going to go through the math, because the math is actually, once you take the log and you take the derivatives and everything, then suddenly you say, oh wow, my god, that's the same thing. So what I'm trying to say is that error minimization in one case turns out can be exactly the same as likelihood maximization in another case, giving it a probabilistic interpretation. So that gives us comfort, right? Because it basically makes us believe, since we get the same solution starting from somewhat different perspectives, it gives us kind of confidence that what we're doing is the right thing, that it's a reasonable form of learning, that we can get to the same equations from maximum likelihood or from error minimization. And it also sort of helps to interpret maximum likelihood. It says that, well, the maximum likelihood solution is also the one that minimizes the error. That's pretty good. All right. Okay. It's 10 minutes. What should we talk about, overfitting and underfitting, or should we call it a day? I think we can actually do these last two slides, because it's only like 2 more slides, and then we'll be done. So we talked a little bit about overfitting and underfitting, and we can kind of think of it in polynomial fitting terms. Like what we're trying to do here is we're trying to learn a mapping from x to y based on these samples, right? So here's the x-axis, here's the y-axis, and here's the samples. And we've got this model, and the model in this case is just a linear model, and we fit the model to the data, and we get something that has some errors, right? There's an error, and there's an error, and there's an error, and no matter how we fit it, this is the best linear least squares fit using the normal equations that we just did. And no matter how we fit that line, there's always going to be points that are in error, because if you rotate the line and shift it up or down, there are always going to be points in error. So rather than a linear model, you could maybe fit a nonlinear model, or maybe you could do a nonlinear transformation, get some newer features, maybe some polynomial features, and then if you look at how the thing that you've learned responds to x, maybe you'd get something that looks like this, right? And this is pretty good, right? You're still not perfect. There's some amount of error here, but you're fitting some points pretty well, and the other points you're not fitting perfectly. But then you do what you were suggesting. Well, I think you were suggesting this. It's like, let's add even more features, or make it an even more powerful nonlinear model. So then what we do is we say, okay, we're perfectly fitting the data. None of these points, it's the same set of data points. We have a very nonlinear model. This is the model, this line, and every single point we fit perfectly well. Right? So arguably, you could say that this is underfitting, this is overfitting, and this is just right. It's like Goldilocks and the Three Bears. This is too cold, this is too hot, and this is just right. I mean, I mean that with not entirely. I mean, it's not clear that this is just right, but you might argue just by visual inspection that this is just right. So what precisely do we mean by overfitting and underfitting? So by the way, so these are example of models fit. So like the left model is just a linear model. The right model is where we add this quadratic x squared feature. So it's just adding one more feature, which is the original feature squared. And this one's adding a polynomial up to 5 degree. So we're adding x squared, x cubed, x to the fourth, and x to the fifth power. And it fits it really well. And these are the actual fits using exactly the same linear least squares equations that we just saw. So more complicated model. We haven't added new information source. We haven't added the number of bedrooms equivalent in this case. We've just squared, cubed, raised to the fourth, and raised to the fifth power, the same x that we started from. And we do a better job fitting because we have a more complicated model, a nonlinear model. But we're still linear in the parameters, right? Because these guys don't change. The linear least squares doesn't care where x comes from. Even so, like in this case, like x would be our z, and then squaring it would be the x, and so on and so forth. All right. So like I said, left is overfitting, so underfitting. So I searched around like what is a good definition of overfitting, and I still like Tom Mitchell. Tom Mitchell is an old machine learning guy from CMU. He's been doing machine learning even longer than me. And he started doing machine learning in the early 70s. And he has this book that he wrote actually years ago, which I still like his definition of overfitting. And basically what the definition says is that we say that a hypothesis, which could be one of these models, one of these linear models, it could be a quadratic model or the fifth order model. He's saying a hypothesis overfits the training examples if some other hypothesis that fits the training examples less well actually performs better over the entire distribution of instances, including instances beyond the training set. So like in order to really know what was overfitting and underfitting, we would really need to see more samples that we didn't use as part of the training set. And if it was the case, for example, like we say that this is overfitting. Suppose we train that thing, but then we get more samples, and the other samples look like this, right? And if in those samples we do less well than this model, then we would say that this guy overfits. And underfitting is the opposite. If this guy does, if this guy does less well than this, then we'd say that this is underfitting. Okay, so that's sort of the more intuitive one. There's also sort of an official formal definition. So given a hypothesis space H, script H, which is the same H that we were talking about earlier, we can say that a given hypothesis lowercase h is set to overfit the training data if there exists some other hypothesis h prime such that h has a smaller error than h prime on the training samples, but h prime, which has a bigger error on the training samples, has a smaller overall error on the true distribution or over all of the data. And in practice, the way we test that is we have what's known as we have a different data set that we don't use during training, which is usually called an evaluation data or development set. And we use the development set to test as a surrogate for the rest of the data. And if it's the case that we find something that does worse on the training set but better on the development set, and something else that does better on the training set and worse on the development, then that thing that did better on the training set is the thing that overfit. That is the working definition of overfitting. So we really don't know. I mean, really just looking at these pictures, we don't know what's overfitting and what's underfitting. We need other sources of information. We need a development set, or we need to have the true probability distribution. Okay, one last compulsory question before we end the class. Yep.
What's the first homework? Or
You-
when will it be posted?
When will it be posted? It'll be posted in a day or two, a couple of days. And so the homeworks are asynchronous with the class. So the homeworks are going to be posted to Canvas. So make sure you check your Canvas settings and make sure you get instantaneous messages or something. And then the homeworks are going to be also due. So basically, we're going to try to schedule the homeworks to be due right after office hours, because usually people like when they can, when the homework is due soon after office hours, so that people can ask questions. Because even though you'll have like a week and a half, maybe 2 weeks to do each homework, I've taught for 20 years. People always wait till the last minute to do your homeworks. This is invariably that will always happen. That will happen in this class. So, do you have another question?
Well, I was going to ask for like a sneak peek of what the topic was for the homework.
Oh, it will be somewhat related to lecture. So it's, you'll find out. Yeah, question.
So, when are we gonna have our lecture video posted on our campus?
I'll try to get it online tonight. Okay. So I have to go home. It takes about an hour on the laptop to process the video, and then it takes some time to upload it to YouTube. So I'll try to get that done tonight. Okay. See you next Tuesday.